Okay, so it's time to start. Well, welcome everybody to the GNU Toolchain micro conference in LPC, which is devoted to discussions between GNU hackers and kernel hackers on issues that may be interesting or relevant for both communities. And I guess that I will have to introduce myself because I have the first presentation in the micro conference. So, well, I'm Jose, and let's start. Let me set the presentation. Yeah, there you go. So let's use the typical approach that we have been using in the conference, which is that at any time that any of you have any question, all you have to do is to switch your video on. And please don't wait, at least in my presentation, please do not wait until the end. So if you have any question, you just interrupt, okay? So is my audio correct? Is it okay? Can somebody confirm? Okay, cool. So let's start. This presentation which is a very short presentation, so we have some time afterwards for discussion. It's about the current status of the support for BPF as a target in the GNU Toolchain. Basically, first, I'm gonna very briefly introduce the project, which has been ongoing for a year, more or less, a bit more than a year. Then I will expose very briefly the current status of the port, which basically means what works and what does not work. Then I will mention also very briefly what we are working at right now. And then finally, I will go through some of the issues and concerns that were raised at the last year edition of the LPC, where we also presented what was then the initial work on this. And then finally, I have like 2 or 3 questions to the kernel hackers on which I need feedback. It's just 3 little things, but nevertheless, I would like to discuss it with you if you want. So the project. We started this like a little more than a year ago with the idea of basically adding support for BPF to the GNU Toolchain. This basically means to make GCC to be able to compile C into BPF. And that will be the first phase, like compiler support, assembler support. Then the second phase that we envisioned was basically to make the BPF programs, which are generated by compiler and assembler, actually palatable for the kernel verifier, meaning that you should be able to run in the kernel the BPF programs that you compile, And then we also envisioned a third phase, which was like, we don't want to stop at, like supporting compiler and assembler and the like, but we also want to provide additional development tools to BPF programmers, which hopefully will be useful for the day-to-day BPF development. So that is the project itself. What is the current status of this work? Well, the BNUTIL support, meaning basically opcodes, disassembler, assembler, and also linker, by the way, it's been upstream since August 2019. It is also now available in Debian and in Oracle Linux 8. In Debian, this is very new, actually. I mean, those packages were uploaded to Debian like a couple of weeks ago. The BNUTIL's BPF package is available in Debian. I think it is in Debian Unstable and testing in both. The version of GNU-Tils in Debian are based on 2.35, if I'm not mistaken. In Oracle Linux, I forgot what version of GNU-Tils we have there. The GCC backend, it's been also upstream since a year ago, since September 2019. It's also available in Debian and in Oracle Linux 8. The Debian package is based on GCC 10, and in Oracle Linux 8, it is GCC 8, 8.2, I think. Then the GDB support and support for an instruction simulator that works integrated in GDB, it's been in upstream since this month that we submitted it, and we worked with the GDB upstream community to get it in GDB master. And well, it basically adds support, basic support for debugging and simulating BPF instructions in GDB. The GDB support is pretty basic at this time. I mean, what works is basically you can load your BPF program, you can set breakpoints, you can single step, and you can access the BPF registers and, well, like reading them, like setting them, and so on. The debugging experience is not yet very good, and this is mainly due to the fact that it is very difficult to support DORF in BPF. And the reason for this is that BPF, as you know very well, is very, very restricted because of security reasons. And the BTF support is not yet in GCC. I will talk more about this later. Regarding the simulator, the support that we have upstream right now is also very basic. It basically, well, allows you to simulate BPF instructions. At the moment, only one BPF program per object file is supported, but we have the foundations in the simulator for progressively emulate or simulate some of the context that the BPF programs have access to when they run in the kernel, starting with supporting different BPF program types. That's the idea. So basically what we will do starting, well, now that we have the basic and the fundamental support in the simulator is to expand it. The end result that we are looking forward to is basically that you should be able to load in the simulator an ELF object file containing BPF programs. The different kind of BPF programs, they live in different sections, which are named following some, well, having some specific prefix that basically identifies the kind of BPF program. And then the idea is that you should be able to run it having some meaningful context for the BPF program. Like, for example, to have some configurable data structures which are passed to the BPF programs when they start running. Finally, in this slide, I have this Deja GNU board, which is basically a configuration for the testing infrastructure that we use in GCC and in other GNU programs, which is also based on the simulator. The main goal for this is that we want to be able to run the complete or a lot of the GCC test suite, which includes tests which are to be run, not just compiled, but also run. So this is the current status of the port as of today. Something else that we are doing in this project, which I already mentioned last year in LPC 2019, but well, I mean, it's getting shape. Basically is that we are adding support to both GCC and the assembler for an extended version of BPF, which is, we call it XBPF or experimental. Again, the name is not important. I mean, some people are starting, well, eBPF, what extended BPF, XBPF is experimental BPF. The name is not important, really. What is this for? First and foremost, we need this so we can properly test the compiler. We think, and for us this is an important point, we think that having just a bunch of BPF-specific tests in GCC is not enough. I mean, if we are gonna support compiling C into BPF, we should try to support as much C as possible. And for us, it is very important because we like to do things well. For us, it is very important that the compiler does the right thing, if not in all cases, in most cases. And for this, it is important that we are able to run as much as the GCC test suite as possible. Unfortunately, BPF is so restricted that the vast majority of tests in GCC, the C-related tests, of course, not the C++ or the other front ends, they don't run, they don't even build. Why? Because they require support for things like indirect calls, they require support for things like sign division, and so on. So that's why we introduced this XBPF. So when you use GCC, if you pass -m XBPF, then some extra instructions will become available. And the compiler will generate them. But not only extra instructions, also other things. Here you can see in the slides that the current extensions we have already implemented. One is support for indirect calls. We introduced an instruction called call R for call to register. This name is internal. The mnemonic, you know, in the disassembly and in the assembler is just call. Also, we have implemented, for example, you know, to save and restore callee safety registers, which it can not be done in eBPF, because eBPF assumes that the set of registers that a function gets from the caller, they have been already, they are fresh, basically fresh registers. You can see here as well a little list of extensions that are coming, which is not complete. I mean, the real list that we have is longer, but just to show you what is this going, where this is going. What are we working on right now? Now we are all busy hacking support for BTF and the compile once, run everywhere capabilities of BPF, which are sort of recent, right? I am aware that we are sort of behind, but in our defense, I have to say that the BPF world is evolving so fast, and well, we don't have that many resources that we would like, but we are, I mean, bear with us. Basically, we are working on support for BTF. The thing is that, of course, when you call GCC, the BPF port of GCC with -G, it should generate BTF debugging information and not DORF. This is something that we have been discussing in the GNU Tools track in this conference, but this basically requires some reforms on the GCC internals, which are related to the way that the debugging information is handled in the compiler. But we are on it, and hopefully this will be available soon, the support for BTF. Of course, we are also adding support for the built-in preserve access index built-in in the compiler, which is used in order to generate the BTF relocations. So the BPF loader in the kernel, well, can do the right thing, right? This is work in progress. So this was a very fast, very quick overview on the project and the current status of the port. Now, in the LPC 2019, where I introduced this project, I got some feedback, which was actually very useful. So let me comment a little bit of that. One of the feedback that we got is that people were quite skeptical in the real utility of having a command line option specifying the version of the kernel. I introduced this option because in my nafty, basically I assume, well, maybe it is important that when you compile a C program into BPF, maybe it is important that you can specify what flavor of kernel you are going to run the BPF program on. So I introduced the option. In that first version of the implementation, this option was used in order to discriminate in what kernel helpers were available to the user. This turned out that it was not the brightest idea, and thank you, for the feedback. So basically, we will see now that the handling of the kernel helpers now is different. The -m kernel option, it is still there, but at the moment it has no purpose in the compiler. Most probably we are gonna remove it but I left it there, just in case maybe it's useful for some other purpose. So that feedback was useful and we actioned on it. The second piece of feedback that we got was that the way that we implemented the kernel helpers, it was not flexible enough. Why? Because what we did initially was to implement the helpers as built-ins in the compiler. And that had two problems. The first problem is that, as someone pointed out last year, it is very common for distros and, well, people in general to run kernels with backports. So basically, you cannot actually rely on the kernel version in order to determine, well, things like what kernel helpers are available and which ones are not. So we changed the way this works. I have another slide later going more into deep on this. And now the result is that the compiler, it no longer knows about what kernel helpers are available or not. It is much more flexible now. Oh, I forgot to mention, that was the first problem. The second problem is that what happens if someone wants to introduce an additional kernel helper on their own, right? Because they want to generate some call instruction to using some specific number. With the previous approach of using built-ins, that was not possible. You would have needed to get the GCC source code to introduce the new kernel helper and to recompile to rebuild the compiler, and that was unacceptable, obviously. And the second problem is also with the new way of doing it, it's also fixed. The third feedback that we got was that we were missing support for the jump 32 instructions in the assembler, and this is also fixed. We added those instructions. So, well, I wanted just to let you know that the feedback we got 1 year ago was acknowledged and it was actioned. Now, I have a little set of questions or issues that I would like to expose to you. First, back to the kernel helpers. The way that the kernel source tree handles helpers is basically generating a file called bpf_helpers.h, which before it was not automatically generated, but of recent it is from some kind of database. And basically each helper is declared as a C function in the way that you can see here. This way of doing it, well, it works, right? I mean, you declare a function prototype and then you assign a constant value, like for example, this bpf get prandom u32, which is the kernel helper number 7. And well, this works well enough, but only if you are building your BPF program with optimization level 02 or probably in 03 as well. But if you build your BPF program with -0, LLVM on one side, it generates an invalid instruction, which identifies the LLVM disassembler. It identifies as call X, which is basically the same thing as the call R that I talked about before in the context of XBPF. And GCC gives you an error. With -02, both LLVM and GCC, they do the right thing. But I have to say that GCC at this point, at this moment, there are situations where it does not do the right thing. Why is this? This is because due to internal compiler characteristics and the way that it works, it is not that easy to basically make sure 100% that the optimizing compiler basically will not try at some point to load the address of the function into a register. And as you can see, it happens in LLVM as well with -0. So then what we did was to replace the old built-ins that we started using, and we replaced them with a new attribute in the compiler, which is this kernel helper attribute that you can see here. With this kernel helper attribute, you can, in your program or in the kernel headers or anywhere, you can basically, you write the function prototype, and then you annotate it with the attribute. And then you tell the compiler that this function, it is a kernel helper. So if you call it, it doesn't matter the optimization level, it doesn't matter the context, it should use the call immediate form of the instruction. The main advantage of this is that it works with any optimization level, and it doesn't rely on the fact that the compiler internally, it does what you think or what you assume it does. We really think that this approach is much more robust than the approach that is being used at the moment. So this is my first question to the kernel hackers. Do you think that the LLVM could adopt this attribute as well? Anybody? Well, okay. Mark, I think that the people hacking the BPF backend in LLVM is basically the same people who work on the BPF support in the kernel. Okay, well, the question is there. At the moment, the kernel is using this first approach, what is now in bpf_helper.h, and we will try to support this as good as we can, but we really recommend to switch to the other way of doing it. Okay. Next question. Sign division instructions. At the moment, BPF, it does not support sign division. It only supports instructions for unsigned division. Now, in one of the frequently asked questions in the kernel documentation, there is an entry which I reproduce in this slide, which is why there is no BPF stif for sign divide operation in BPF. The answer which is documented there is that it will be rarely used, and LLVM errors in such case and prints a suggestion to use unsigned divide instead. Okay, fair enough. However, it seems to me that if the BPF hackers felt the need of including an entry in the frequently asked questions about this, it seems to me that maybe it would not such rarely used, because if it is only rarely used, then why is it a frequently asked question, right? I mean, that on one side. On the other side, the current behavior of LLVM is basically to emit an internal compiler error, which actually, by the way, is asking the user to submit a bug report. And this probably should be fixed. And the current behavior of GCC is that it emits a compilation error. Obviously, the lack of sign division is not just a detail. I mean, unsigned division and signed division are completely different operations. But the problem that this introduces for us is basically that the lack of sign division, it breaks C very much. And for the same reason that I mentioned before, that we really want to be able to test this backend properly, this is a big problem for us to run the GCC test suite. So what we did was to add support for sign division and reminder to XPPF using the opcodes that you can see in this slide here, which, by the way, introduces an additional problem that we will see in the next slide. So my question to the BPF hackers is, will you please reconsider supporting sign division in BPF? Yeah. Lawrence mentions that adding support for new opcodes is tricky since you need to deal with the JITs in the kernel. Yeah, I understand that. Yes. Yeah, that's true. Still, I think, I mean, for us, this is not an immediate problem because of XPPF, and we ran the GCC test suite with XPPF. But I think it would be nice to have support for this in eBPF proper. This said, I mean, I'm not a kernel hacker, you know. I mean, I can't actually attest, you know, to the. I don't know exactly, you know, how useful will have to be sign division in real world, real BPF programs. So I was hoping that maybe someone here could provide some feedback on that. Anyway, whatever. This is another question that we threw. Another question that I have is that we are extending BPF, the eBPF proper, with new stuff, and we are calling it XPPF. But while doing so, we are introducing new instructions, like the sign division instructions. And those instructions, they need opcodes. Now, there is a potential problem here, which is that what happens if we use, for example, for sign division, we are using this op class in the ALU, both the 64 and the 32 bits versions. We are using those opcode classes. This could be problematic if at some point eBPF gets expanded in the kernel and they use the same opcodes. So for that, we think that it would be interesting to reserve some of the opcode space in the BPF instruction set for extensions. So basically, the contract would be in that range, the BPF in the kernel we never used, and extensions like XPPF or maybe other extensions that may pop up in the future somewhere else, well, it will be available for that. I looked at the instruction set, and I have to say that there are not many opcodes left. Basically, there are some instruction classes that are pretty much exhausted. The ALU and ALU64 classes, they only have 2 available opcodes each. In those 2 classes, they have the characteristic that when you add a new arithmetic instruction to one class, you definitely want to add it to the other class, because those 2 classes are implementing the instructions that work on 64-bit operands and 32-bit operands. For the jump instructions and the load store instructions is a bit of the same. And it is in the LD and ST instruction classes where we have more room. So the question is, could we reserve a range of and document it of the BPF instruction set and reserve it for extensions? Probably the way to go here would be to use the load or the store classes and split them. Well, okay. Well, basically, those were the three questions that they had, and they was wishing to discuss. Maybe we can do it afterwards in the mailing list. Yeah, that's what Lawrence is suggesting. I agree. And well,
we have a representative from LLVM. I called Nick, and I don't know if he knows the answer. If you can go back to the slide with the
okay. Yeah. So, who is this person? Sorry, Nick.
Hey.
Ah, hi. How you doing?
Hey.
So,
sorry, what was the question?
Well, the first question is if you will be willing to add support for a function attribute like the one that you see in the slide that you can use to. We have this implemented in GCC, that you can use it to mark a function prototype as a kernel helper explicitly, including specifying what is the ID of the kernel helper.
Sorry, and what's the number that gets passed here?
The number is just an integer that identifies which kernel helper, which at the end it translates into the immediate that gets passed to the call instruction.
I mean, sorry, to be honest, I don't really know what this gets used for in BPF, but you know, I think just having do you have a RFC or anything written up of what this would be like? How this is useful in BPF. I think that was the first thing that, you know, I can take that and share that with folks working on BPF in LLVM.
Mm-hmm. Well, okay, I can write it up. The second one was to support sign division instructions in BPF. But you know, this is not that as much as LLVM relevant as to BPF instruction set relevant, basically. Actually, so well, and the third one was to reserve a range in the BPF instruction set in the opcodes for extensions. But then again, this is not that much LLVM relevant than BPF relevant.
Yeah, I think the sign division, it sounds more like first getting buy-in to use that high-level instruction, and then, you know, I think LLVM is probably just, maybe it's just unrecognized kind of instruction for LLVM, not necessarily that they're trying to prevent it.
Oh, and now that you are here, well, basically we have a simulator for BPF that we introduced upstream like this month. And one of the main reasons for that is that we want to run the GCC test suite using the simulator, right? I guess you are familiar on how the GNU uses boards and simulator boards, right? To run GCC on targets that are simulated.
Oh, sorry, I'm not familiar.
Well, how do you do it in LLVM?
For running the compiler itself?
Well, the thing is that if you, for running the compiler test suite, when you are testing support for some target, like a cross target, for example.
So typically we have all the backends enabled, so we can generate code for them. I'm not sure if you're asking about cross compiling in general, or then running
No,
the cross-compiled code.
about running the tests.
Oh, yeah, I don't think LLVM has tests like that, but I could be wrong.
Okay. Well, I was gonna just let you know that with the simulator, if you wanted to support that, you could use it, but okay. Okay, thank you. All right, so this is all I had. So we have time for questions or whatever. No? Okay, well, thank you for your attention. The next presentation is in 10 minutes.
So wait a minute. Let's decide what we're doing from here. So we should email the BPF people on the mailing list.
Mm-hmm.
Yes.
Yeah, sure. Yeah.
Yeah.
I will follow up with emails to the BPF mailing list.
Okay. Thanks, Jose. Oh, nobody took notes. Oops. Not a lot of notes to take. There was no discussion, so.
Hey, about translating dwarf to BTF. So BTF only does types, am I right?
Yes, that's correct.
Okay, so then, for example, you will throw away the whole line table.
Yeah, pretty much.
Okay. Is there anything that you could use for stepping through a BPF program if you don't have dwarf?
Yes, basically, and that is part of our schema. Basically, what you will do is that you will build your BPF program with -m BPF, -mx BPF, which will use dwarf, and you debug the program in the simulator.
Okay, yeah. Okay.
And then, so you get, call frame information and everything, you get all that stuff. And then when you are happy, then you rebuild the program without as proper BPF, not XBPF, and then you deploy it or whatever. Yeah.
Okay, so by default, -G generates BTF, but if you are generating XBPF, then you also add dwarf.
Yeah, that's the idea.
Okay.
I mean, the reason is not that we do not want to support dwarf, is that BPF is so restricted that it's simply no way to do it. Like take call frame information, for example. In BPF, you cannot access the stack frame of the caller using a relative offset relative to the frame pointer. You can get a pointer into the stack frame of the caller, but you cannot access it relatively. So implementing CFI, I don't know how could that be achieved using like normal restricted BPF. No. I think that the BPF people, they have been talking about supporting some sort of stack traces, but in the kernel. Inside kernel. Okay, so we are 4 minutes to the next talk. The next talk is Nick, right? Right? Let me see the scale. Yes, it should be. Yes, CTF as a possible BTF data source. So, Nick. Hey, there you are. We can't hear you. Well, at least I can't hear you. Are you mute? You are not mute, but now it works.
Wrong recording stream. Sorry.
Yeah.
I don't know why it decided to get recording streams and playback streams from different places. Is my audio all chopped up and horrible? I hope not.
It's very good.
Different from last time then.
Yeah.
Well, I've got lots of questions for the BPF people as well, so I suspect I'll get the same sort of answers you did. We'll see. Well, that means we just do whatever we want.
Right.
3 minutes.
Okay, 3 minutes, yes.
Turn off. Through the sound. Okay. Might as well pull the slides up.
Yeah, let me do that. There you go. CTF, BTF. Yeah. Can you check quickly if it's the right version and everything? Oh, let me give you presenter.
Yeah.
Superpowers. Where is this?
Probably do need to be able to move around.
Yeah. Now you have.
Oh, the power slide. That's more or less the area that got changed heavily. Yes, although in hindsight the arrow is not actually dense enough.
Oh no!
Oh, a disaster! Yes.
You can paint them using this.
Yes.
Yeah, it works.
It's got a flood fill. I probably could. It doesn't matter.
Okay, 1 minute.
Actually, I think it's now 45. So let's get going. This is a brief catch up on the state of CTF since last year. It has made progress, saying where it's going. and suggesting an alternative way of interoperating with BTF, which might help reduce the amount of code that BTF needs to the BTF people need to maintain. There are also several possible attack vectors there. None of this is for the next 5 minutes. In fact, it's probably not even for the next year, since some parts of the CTF side of this haven't been finished yet. But they will get finished in time. The whole of last year was more or less filled with getting link time deduplication working and adding infrastructure that needed. It works. I haven't spent a great deal of time optimizing it, but it's already in the noise for virtually all links. Even monsters with huge numbers of types like Nouveau KO it takes only sort of 15 seconds to optimize everything. It's good enough at deduplication that your average program seems to end up with less CTF than there was in a single input translation unit. Not all of them put together, but any given translation unit of the on the input, which is kind of what you'd expect, because most of the types are going to come from header files and would be shared in any case. We are doing things that I haven't seen any other deduplicators do, other than possibly some dwarf deduplicators, including things like handling cases like types in gigantic cycles, where parts of the cycles are only visible in single translation units and other parts have different definitions in different translation units. We will deduplicate that reliably. GNU Tools has some in it. I don't think BT even tries to handle types with different definitions in different translation units. It doesn't seem like it would be terribly useful for its major use case of getting task struct and the other shared stuff working. But we do handle it, and it doesn't slow us down. What's coming up? I have a link to a to-do list there. I try to keep it up to date. Yesterday I just pushed something get textizing libctf. Nobody cares yet because there are no translations, but now there could be translations. I'm working on sim-tab handling, so you can hand in a symbol table offset or a symbol number and get the type of that symbol back out, or the prototype of that function back out. But in addition to the things in the to-do list, it would also be nice. Parhole has machinery which can take BTF and T-code. I think CTF thing. It wouldn't be very difficult. It would go in libctf, so everyone would use it. And I have a use for it later in this talk. The other major thing that's coming up is a format bump of libctf. Format v3 which has been around for a year or so, was focused on dropping all the range limitations in libctf. Sorry, in the CTF file format, so we can now handle billions of types and that sort of thing. But it did lose some compactness at the same time. I'm bringing that back. I already know how to do that. I'm also doing things like trying to do things like delta compressing big structures. So if you've got one structure which is just like another one but with a couple of extra members, you don't need to store the couple of extra members. If you've got the structures where all the members have names with the same leading element, we'd only store that leading element once, which is very common in C. I'm thinking of changing the way we handle parentage, that way we handle ambiguous types, and saving lots of space. So they came up with an improved approach there. At the last LPC, people wondered if we could represent GCC type attributes. We can't yet. We will. Format V will add it. There's also in Format V3 there is a variable section which lets you map from names to single types. This was added so that you could look at the types of static variables in the kernel. The kernel people said, what about function prototypes? So I had to say, we don't do that. I'm actually dropping the variable section because it turns out that we can do everything we did with the variable section with the sim-tab lookup code, except instead of looking up symbol table offsets, you look up names instead. And if you can do that with variables, you can do that with functions. So this will also give us what was asked at the last LPC. We can look up map names to functions and get back the function prototype. There was also a request to record the argument names in function prototypes, which, while it's not part of a type system, it seems really useful. So I'm going to add that as well. And one last extra is to add LZMA compression, which should give us a massive pile of compactness for free. The question is, what happens if users don't have liblzma? We can rely on always having zlib. Things are currently libz compressed. We can rely on always having that because it's static, because it's provided in GNU tools and compiled if not already available. LZMA isn't. There are already things in GNU tools that use LZMA, so they must have a fallback. I guess I'd do whatever they do. But one plan I had last year may not be working out. I wanted to have this utopian idea of reading and writing every single CTF-like format that had ever been implemented, including all the CTF-like formats on other operating systems, all the older versions of CTF that we'd implemented, and so on. I still want to do that, but one of those formats was BTF. And BTF, as far as I can tell from the BTF mailing list, changes all the time. There seem to be multiple format bumps. There seem to be multiple format bumps a month. GNU tools releases every 6 months. libctf the kernel releases more often than that, and you don't have to update GNU tools in sync, and no one ever does. So I don't see how we could even if we kept up to date with the latest BTF at the time GNU tools was released. I don't see how you could guarantee that will be available for the kernel. We would probably only ever be emitting the BTF format that the kernel saw as an old one. And I don't think the kernel retains backward compatibility, so it wouldn't understand the old format. So it seems, even though we could emit BTF from libctf, it seems pointless. We could only emit BTF that the kernel wouldn't be able to use. I would like to be able to interoperate by directly giving the kernel BTF, because that would mean almost all a lot of the BTF code in the kernel can be massively simplified, or in the kernel's build system. But that doesn't seem practical, unfortunately. I wish it was. If anyone has a suggestion for ways I could make it practical, please say. But I still think we can help. Here's one wild option, one wild possibility. BGF operates by converting dwarf into C code, and then generating BTF, compiling the C code and compiling the C code and then generating BTF from it, or part of the compile once run everywhere machinery does. We can do something similar. We haven't got the code yet. This is something I talked about in an earlier slide. We could emit C code from compiled from the CTF, which the compiler will generate, and the linker already deduplicates. We could turn that back into C code again as a bunch of type definitions. Those type definitions would already be deduplicated, so you would not need a BTF deduplicator at all. It's a couple of thousand lines you could throw away. In fact, we even do things that I don't think BTF even needs, which the next couple of slides handle, which is to distribute types across multiple CTF dictionaries, which would be represented here as emitting multiple C files, most of which would include a parent, the shared dictionary. We have 2 different ways of distributing types. Here's an example. There's an arrow in the middle if you can't see it. The left-hand side is the source, and the output side is the target dictionaries. This is what is used for almost all normal programs. It provides most compactness, but if you have a very large number of types, you might end up with a lot of types you're not referring to in the shared dictionary that is loaded all the time. This moves every type which isn't ambiguous into the shared dictionary, and in this case only struct foo, which is a struct in one TU and the U16 in the other, ends up in per module dictionaries. If there are types in cycles, the cycles are broken, and only a minimal subset gets moved into the per module dictionary, so this isn't too bloated. The other approach, which uses more space, is currently what we're using for CTF in the kernel in our local patches. Is to also move all types that only appear in one kernel module into a per module dictionary. So you don't need to read them in if you're only looking at the shared dictionary and a couple of modules. Uses more space in the resulting output, but probably means you have to read less in. In the kernel at the moment, we have about 1.5 meg of CTF in the shared dictionary, about half a meg in the dictionary for VM Linux, and about 9 meg in per module dictionaries that just aren't read in normally, more than half the types. So it does save time, even though it makes the CTF bigger because types are duplicated more. We can generate either. It's just a linker flag. We could generate different ones. We can generate things differently again if you'd like it. We can have more schemes for distributing types. The C generator would be the CTF to C generator would spit out 3 C files in this case and 4 C files in this case. Probably the per module ones would hash include the shared ones, and you could just compile whichever ones you like, or just ignore all the per module ones and compile the shared one to get BTF out of it. This does have the advantage that this completely decouples libctf from BTF format. All we do is spit out C, and BTF can just read that in, turn it in whatever way is necessary into BTF, and trust that they're deduplicated. You can throw the deduplicator away, which saves a few thousand lines of fairly complicated code. You can also trust that the strings are already deduplicated, although I suspect you'd still need some kind of string deduplicator in there, simply because you might accidentally reduplicate while you were pulling things in. This seems plausible to me. There are other approaches, like since libctf is a library, like having a little tool which reads the CTF directly using libctf and generates BTF. libctf has a stable API which will not be broken, so you can just stick with that. That's just as practical, and you could have that tool in the kernel source tree, and that would also keep libctf decoupled from the BTF file format. The other alternative is to keep BTF stable enough that we can emit it directly, but this seems a little unlikely to me. I'm happy with any of these options, but I might be able to help out in some way, and at the moment the BTF just moves too fast. So would either of these options be practical? Is there some other way I could help out so that you don't need to maintain thousands of lines of deduplicator and so on and so forth when we're already maintaining a deduplicator and verifying that it works for all of user space? Hopefully it's going to end up much more tested, much more of a code base to test it on. Can we do anything else? Are there any format enhancements that might be helpful? Is there something BTF is doing that you think CTF might be able to do? Anyone got any suggestions? If there are any BTF people even here?
Well, if we include line information in CTF, then we just use CTF and not BTF.
Yeah, the problem is the kernel has in BTF readers and so on. We need to generate BTF somehow. There was a suggestion last LPC of generating a no malloc CTF reader so they could use it in the kernel. You'll note that's not on this slide. I've got so much else to do. It's miles away in the future. It's possible, but I haven't even thought about it yet. Also, the whole license nightmare gets involved at that point. So GPL v2 versus LGPL and so on and so forth. libctf is and will always remain usable by kernel build tools. There will never be a license problem there. Does anyone have any suggestions? We've had half an hour. Otherwise, I'll do whatever seems right and just hope that the kernel team, the BTF people don't say we're not using your stuff and go away. It would be a right waste of time if that happened. Avoid that, but if no one's here, no one's here.
Okay, I will make a question because we have the time and why not? Do we have in CTF, I guess we do, but have you seen what the BPF people are doing with the C bitmaps, for example, with BTF and compile once, run everywhere?
No.
Well, basically, I'm curious is that if it will be possible to do the same with CTF instead of BTF, if we have enough information to do that. I mean, to implement the core code stuff with CTF.
Well, all you really need for that is the offsets of things in structures, and we certainly record that. The whole relocks stuff, obviously, we're not including relocks of any sort, except insofar as structure offsets count. Maybe you could add some diff CTF against other CTF. We'd need that for the delta compression stuff anyway, which would let you find out where how two structures differ and what offsets relocks you need to apply to turn one into the other. But at the moment, I think you could do that with a simple subtraction. I haven't been paying attention to what's been happening on the BPF side, which is I was hoping this talk would let me catch up a bit. I'll obviously have to do some research.
Yeah.
Well, if there's dead silence and there are no BPF people or BTF people here, I guess that's it. I guess everybody gets a break. Anything? Okay.
Well, maybe kind of a similar question as I had last time. So for the CTF generation already works for all user space.
Well, all user space I've tested. I haven't yet done a full distro rebuild. That's coming soon.
Right. So is it useful on its own? I mean, if we remove Dwarf.
Yeah, it will. The thing I'm working on now, looking up syntabs, going from syntab offsets to types, is probably necessary for it to be useful. That will certainly be in before the next GNU Tools release. Once you've got that, you can and corresponding GDB support, you could go from a simple table entry and ask what type is this.
Right. So then
useful.
Yeah. So then you have something that is useful, for example, for libabigail to generate its reports, its ABI reports.
Oh yeah. That was one of my use cases. Another completely mad one, which I mumbled about in the LWN article, which introduced all of this, was a wild future in which shipping header files would no longer be quite so necessary, because C code could interrogate the .cts section in shared libraries and find out what was available after they de-opened it, and assemble function calls and FS call them.
Yeah. No, but it's I'm thinking of use cases where you don't want all of Dwarf, but could maybe just stick with CTF. An unwind table is probably needed, but then you already have profilers, for example, are probably fine with CTF and an unwind table.
We're writing a backtrace section at some point, which should probably have something like a line table in it, with an emphasis on being on compactness, but without the need for the incredible complexity of dwarf expression expert lock handling. There is CTF is much more compact than dwarf. I mean, people told me when I started working on this, just use dwarves. Dwarves could often chop 50% off the size of dwarf. You might go from 10 meg to 5 meg. That was for GNU LD, when I was testing it with GNU LD. The CTF for GNU LD is 87K. Rather radical difference. Of course, it doesn't store and encode as much as dwarf does.
But for the unwinder, you probably need much more than what's actually supported in the official ABI, because GCC does change the ABI for local functions.
We're not. Sorry, is this? Sorry, I didn't quite catch that.
You can't throw out everything in Dwarf and just use C types. Like,
yeah.
for calling convention. So GCC rewrites calling conventions for local functions, not to use the standard ABI.
Yeah.
So you need some of the complexity in Dwarf that Dwarf uses to describe arguments and stuff like that.
I'll admit that one thing which is not on the obviously I actually audited all the Dwarf in, I can't remember which distro it was now. I think I picked Gen 2 Arch and FreeBSD compiled with GCC and compiled with LLVM just to get a sort of vague overview. And a lot of the complexity in Xplox is used by C++, but at the moment CTF is C only. And it's amazing. And if we're aiming to represent 99% of call or 99.5% of call, which is probably enough for most uses, because GDB fails more often than that, half the time when doing a backtrace. If you're aiming to be able to represent 99 and 99.5%, we don't need most of the Xplox complexity. I think we can a few fairly simple literals to do the trick. But this is still up in the air. We're still designing. The last design I did was a pile of stuff. Email was sent out a year ago. I've been working on the deduplicator since then. This is all stuff we're still thinking about. We think we can drop a lot of the complexity for most cases. Obviously, if you've got a massive complicated C++ program with virtual basis, it's Dwarf or nothing. But in the simple cases, which is the majority of cases, we think we might be able to just to save a pile of space and come up with something simpler. And we're making it part of CTF at the moment because it's a new section in CTF, and CTF can evolve easily right now. Or it's something that uses CTF or something like that. I have no objection, by the way, to Dwarf starting to steal bits of CTF and calling into CTF and that sort of thing in future releases. I don't know if it's useful, but I would be amenable to it and to making changes to make it easier for other things to use it. It remains to be seen. I still have to turn the tech info specs for CTF into something in GNU Tools upstream first. There's also going to be a manual for the actual API coming up, but that hasn't even been written yet. But yes, I agree. I agree that the Dwarf Xplox complexity is not there for no reason. Some things really do need it.
Yeah, but still there are degrees, because just to provide a bit of context, we started thinking about adding backtracing support to CTF because we got a requirement from one of our internal customers in Oracle, because they have an online backtracer, a custom one, which is they wrote it themselves, but it is very, very ad hoc. I mean, it knows about the architecture, and it tries to do the parsing of function prologues and epilogues by itself. But the problem that they have is that every time they upgrade glibc, it stops working, and they have to modify it again. So they were looking for something that they could use, that it would be like more generic and something that they would not have to maintain themselves. But then they were not happy with the idea of using Dorf because of two main problems. On one side, Dorf is very big, and it requires non-trivial infrastructure in order to, for example, execute the Dorf expressions, which are denoting the different values that you have in the call frame information. And they did not want to have to actually ship with their program a Dorf interpreter, right, for that. So they wanted something simpler. And then the other main reason why Dorf was not suitable for them, it was because they thought that Dorf was exposing a lot of information that they did not want to expose to the customers, right? So that's why we thought, well, that means that we need something else, right? We need like some kind of format, debugging format that is suitable for this kind of online operations, like a backtracer in a running program, something that you can have in your own code, basically fulfilling those requirements. And since we were working on CTF at the time, then we thought, well, why not using CTF for that? That's the context.
Yeah, so on the C++ side, I haven't really even begun thinking about how much of C++'s type system it would make sense to include in CTF. I mean, how far rabbit hole do you go? Templates disappear at runtime. Does that mean you don't encode them? Does it mean they're useful to encode? So much of the C++ stuff would turn CTF into a flaming nightmare. I've been trying to avoid it. Obviously, class representations, class relationships we would want to encode because they appear at runtime. Given that we can already encode structs and unions, I don't think classes are likely to be that difficult, all things considered. But C++ has a lot of other stuff in it. I don't know how much of it makes sense to encode. I haven't even started thinking about it more than idly. There's been too much else. One thing that is the case is the deduplicator will almost certainly work for C++ with hardly any changes at all, because it's the main constraint for the deduplicator is which things in the type system make the type system cyclic, and I'm reasonably certain that C++ has exactly the same things as C does that would make it cyclic, which are the classes. Thank goodness the deduplicator is certainly the most complicated part of libctf at the moment. But that's all I've got, really. We could have a break.
Okay, thank you, Nick. So,
Okay.
as it happens, we have a long break now until okay, because I'm a bit confused because we have so much time now until 8:40.
just a note. Yeah, no, I don't need presenter. Just a note that I tried some string optimization last year in what turned out to be a failed experiment. I tried what I can only describe as identifier-aware chunking of all the strings in the CTF, slicing the strings into chunks of underscores and changes from lower to uppercase. The idea being that you'd slice the identifiers into sort of word-like chunks and turn strings into a list of chunks. It saves a lot of space. It saves almost half the space in the CTF, and then you compress it with zlib, and the space required goes up. It turns out that compressors are better than ad hoc. Generalized compressors are better than ad hoc compressors in that case. All the indexes in the chunks table blew up the space needed at no end. It was most unfortunate. I'm trying in format v4 a much simpler approach, which avoids the chunks table entirely, simply saying that if within a given structure, all the structure members have a common prefix, which is fairly common in some C structures. We encode the prefix separately. Because there's no pointers for that prefix and nothing like a chunk table, we just add it to every field in the structure. That should save space even with a modern compressor. But anything which involves slicing strings up and storing chunks to it will be a disaster area as soon as compressors get involved. The compressors do a better job than we can, or at least they do a better job than I can. Yeah, this is probably something worth noting for Dwarf as well, given there's GZIP compressed Z-debug these days. All of CTF is designed to try to avoid too many indexes to other types, because every time you've got an index of any kind, it's an relatively uncompressible symbol. It depends whether you're aiming for saving space in memory or saving space on disk. And CTF is definitely going for saving space on disk in the compressed representation because we're not stripped out. I suspect Dwarf is going for saving space in memory over that because they can be gigabytes long. We already, CTF already sorts all of its string table into alphabetical order as a crude way to improve compression, deduplicates it, and eliminates all strings from it that also appear in the ELF string table and points to the ELF string table instead. The problem is that structure members names don't appear in the ELF string table, and there are a lot of them.
I was muted, wasn't I? So with the ELF string table, do you mean the SimTab string table or the debug string table?
It's the SimTab string table. It's tab. The debug string table has often been stripped out when CTF is used, so we can't rely on it.
Okay, but isn't the SimTab also often stripped out?
I can't remember which SimTab we use. We use one that's almost always there. I don't think the SimTab. I checked, and the one I ended up using is not stripped out by strip. I can't remember which one it is.
Yeah. So you have the dynamic string table, which is kept for shared libraries. For example, you have the SimTab, which is often stripped out, but not always.
We use the associated, whichever string table is associated with the symbol table.
Yeah, but you have two symbol tables. You have the DIN symbol and the SimTab. Yeah.
But yeah, we let ELF work that out basically, because whenever I tried to make a decision, I got it wrong. And this seems to come to the right conclusions with shared libraries and with binaries. So it's tweakable. It's the symbol table that seems to have most of the useful content in it.
Yeah, and I assume you never strip out CTF itself.
No.
Yeah.
No. The whole point is to make this so small that you don't need to. And it's smaller than most of the other help objects. There are a couple of edge cases in my table where the CTF bloats horrendously. GhostScript is a nice example. We end up with about 4 meg of CTF. This is a format limitation which will be lifted in V4. It's nice to have a few cases where V3 doesn't work, so I can be sure that V4 can improve on them.
And do you load the CTF segments in memory, or are they only always on disk?
They are not. I may as well turn the webcam on. They are actually not usable unless they're loaded, because part of the loading process involves stepping over all of the CTF type section. It decompresses it, steps over it, and constructs indexes in memory of things like array offsets, which are not recorded in the CTF itself to save space. This actually uses no time at all over decompression, because I think because we're almost always cache bound. And the CTF is small enough that it doesn't cause a problem.
Okay. Interesting. Yeah. So I have been thinking, especially for C++, the symbols in the SymTab are often the same huge, yeah, and the same you want in the dwarf. And currently you have the debug string and the SymTab having lots of the same strings. But the problem is that they might not actually be in the same file. So, yeah.
The CTF approach, for what it's worth, is to slice the string space into 2 halves. And the most significant bit says, look in the old green string table, which is normally the L string table. And everything else is just a strip-tab offset. It works. At one point I had it sliced into 4 pieces when I had the chunks table experiment, but at the moment there are just 2.
Okay.
Nice idea from the Solaris people.
Yeah, but maybe that could be an extension to dwarf, that you have a string form which says this is an index into the SymTab.
Or the other alternative, which is even weirder, is to simply say, okay, well, once we've built these things, they don't change. So we just conceptually append the 2 string tables and make and just have it as if one runs off the end of the other and just make the offset bigger. That doesn't work. It comes down to what compression is better.
Well, what you could do is have something like DWZ rewrite not just the dwarf but also the SymTab and make them share the same. I think that might actually work.
If DWZ rewrites the strip-tab, you're going to break the CTF. It's got pointing to it.
Okay, so then we have to make.
That's easy for DWZ to deal with. It just needs to read the CTF in and then write it out afterwards again. Without
simple.
Because we deduplicate and re-emit the string tables every time we do the write-out. So. It is only a few function call from the CTF.
Okay.
So it's not too painful. I am very happy, by the way. DWZ was far faster than I thought it would be. I'm just unhappy at the number of times it isn't able to shrink gigantic piles of debugging code. I don't know why. It does a fairly impressive job of shrinking given what it's working on. But I wish it could trill the debug info by more than not at all. I don't know why.
You mentioned unwinding earlier, and it seems that the decoding for CTF requires memory allocation.
Oh yeah, we're not even trying to make a malloc-free version, at least not at the moment.
Okay, so that puts sort of a dent into the unwinding.
Oh, yes. The idea there is that the allocation happens long before the unwinder kicks in. You do that at load time. The actual unwind better not need to do memory allocation for obvious reasons. One crazy idea I thought of was to have to try to segregate CTF from this process in the middle of unwinding in God knows what disaster state, is to have all the actual unwinder in a sub-process, and all the crashing process does is chatters to it over a pipe using raw syscalls. It might work.
Yeah, I mean, that is what some people try to do when they fork on a segmentation fault, right? But we can't really support that in glibc for various reasons.
Hoping, what I was thinking of was if you knew if you know this program could invoke the unwinder, you either preemptively fork off the unwinder, or you have an unwinder daemon running you can just connect to, a sort of unwinder service, maybe via a debus service or something like that. So that you don't need to fork, you just got a pipe you can chat about.
Yeah, I mean, they're like there are like 3 applications for unwinding, or many more obviously, but the 3 main things I see is the crash case, then pthread cancellation handling, and then C++. Exception handling, yeah. C++ exception handling, and pthread cancellation is similar, but you can't really tell if a C program is going to use it or not beforehand. It's sort of, it happens or it does not happen. You don't really know.
Yeah, well, frankly, I care about C++. I tried to use pthread cancellation once and came to the conclusion that anyone who was using even the synchronous version was mad. I suspect it's becoming so rarely used that adding features to it is totally redundant.
So I think that there are a couple of developments here. Anyway, so my point was that the crash handling case
which I care about,
is something we think is solved by the kernel and its out of process crash handler, where you nowadays can map the process. The crash handler can map the process image that has crashed and examine that before it's written to the disk as a core file, and you can then you can basically do what you want there.
Oh, that's very nice. You don't even need to change the program. Ooh, I got it like that. Okay, that goes into
it's a zombie at that point. It's a zombie at that point, but it avoids all the nasty issues where the crash handler itself does crashes again, or it destroys.
It's a zombie. That means it's not mapped. Can you tell what it was when it was mapped, or has all that stuff disappeared? Because it would be nice to be able to dig out.
No, you have the proc file entry is still there, and you can see everything that's been mapped.
Oh, good. Well, that's all we need then.
So it's basically all there, but it's like a core file that hasn't been written to disk.
Because one of the things I ran into last year, Solaris has this insanely complicated scheme with embedded serial number in every section and so on and so forth to handle a case where a binary that was unlinked has crashed. You don't need any of that on Linux. You can just open proc.pig map files, individual mappings from there, and you get the mapping back even if it's been deleted, which is very useful for crash handling.
Yeah, that is a fairly recent feature, and that also ties into the crash handler support. So
that's a very nice, very good.
Yeah,
that's definitely how it needs to be implemented.
and I think that at least that's in my opinion, that covers the crash handling case. It's separate. It's more robust than doing it in process. You don't have to do stuff like forking off the crash handler or anything like that. So basically, that leaves exception handling in various forms.
Yeah. Although it occurs to me there is one extra feature that would be nice there, which the kernel doesn't have. It's a kernel feature, so we can't do much about it, which is that at the moment, changing the crash handler requires sysadmin attention. What we actually need is for it to be a process attribute, so the process can say this crash handler, and it gets set up for that sub-process tree only.
I think there are some people have patches which make it basically a namespace property. So you spin off a new user namespace and then you can set the crash handler. But I'm not sure if that's in mainline yet.
It's probably overkill.
Yeah.
In practice,
No,
stuff would be sysadmin anyway.
It makes people really want to the relying on systemd code dump control for catching the code dumps is probably too disruptive a change, and people want to keep their own old crash handler they've maintained for 20 years. And being able to
obviously for our use case, a certain gigantic database. There's going to be sysadmin attention when you install that monster anyway, so setting up a new crash handler would not be very difficult.
Yeah. No, what I'm interested in is basically trying to unify the C++ error handling and make exceptions available in all contexts. Currently, we have the issue with C++ signal handling that even if you catch the exception in the same signal handler, that if you catch an exception before it exits the signal handler, if you're running a signal handler, then it's still not async signal safe. What you can do today is, if you get a synchronous exception like division by 0, then you can throw from the signal handler, and it unwinds correctly and reports the signal, the exception at the point of the instruction. If you build with fnon-call exceptions, that is. Same for null pointer dereferences. So for synchronous exceptions, we can already unwind through the signal handler, and obviously for debugging purposes, we can do as well. But what we can't do is, if we get a synchronous exception, it's not safe to invoke the unwinder for various reasons. One is glibc has logging that's going on, and the other stuff is like memory allocation in the unwinder and a bunch of other issues. And for my interest in this area is that I'd like to see eventually some sort of blessed C++ interface for POSIX that actually uses more.
I haven't been thinking much about C++ exception handling in this context, and as I don't think the more complexity you add to this not yet designed CTF unwind section, the bigger it gets. But or backtrace section, it is perfectly possible to have a CTF backtrace section that calls into that has references to Frame or vice versa for all the nasty stuff, and so the simple stuff goes in a more compact section, and the nasty stuff falls back to what's already there. We haven't designed any of this, but it seems possible for some bit of space, in theory.
Yeah, for C++, you could always for the actual unwinding for exception purposes, you can always do the stack transformation or the state transformation using actual machine code.
Yeah. I mean, the primary purpose of this was to backtraces. So that, the primary purpose of this was to get BT working in GDB and backtraces in logs and that sort of thing. But if we can help with the C++ unwinding case as well, why not? Yeah. I just don't think we'd be able to handle all of it, so we'd end up funking down to the existing machinery for some of it. But that means some of the existing sections could shrink. So.
Yeah, but if the unwinding could be supported by machine code, then then you can actually do arbitrary transformations, I suppose. And it might not be, and you save the dwarf interpretation overhead, obviously. Anyway,
we have to wrap up because
things to think about.
Next presenter is already here.
Okay, I'll disappear.
Thank you, Nick, and thanks, Florian, for your comments.
Nick, can you take some notes in the share notes about this whole discussion, make a little summary?
Sorry, I didn't hear that.
If you can type in the shared notes in big blue button, you see above the user list, there is a thing that says shared notes. If you can type up some of the stuff.
Yeah.
Thank you.
On that.
Hi, Kiss.
Hello.
Okay, the audio seems to work properly, the video as well. You got your slides there, and you are presenter.
Awesome. I got
like looks like less than a minute or so. I'll
Yeah, 1
pause
minute.
just for a second. Alrighty, it's 8:40. Well, for me 8:40. It is 40. I'm going to go ahead and start. This is some of this was actually covered earlier in the week by Serge Goulton. Perhaps I've mangled his last name in the GNU Tools track. I cover a slightly different subset and have a little bit slightly different focus on where things stand. This is mostly a continuation of the similar presentation I gave last year. I'm going to try to do a comparison between last year and this year. And I've tried to fill this up a little bit with a lot more links back to like bug tracker issues and discussions and anything. So each particular feature set, there's a little bit easier to sort of get into looking at the history of it or participating in it. So I'm ignoring a bunch of these sort of features that I sort of view as being at parity between GCC and Clang. One odd exception here, of course, is the Spectre v2 mitigations, which they are at parity, but they don't have the same arguments. But that seems to be kind of an endemic problem. So this is sort of the summary of the things I'm going to look at. And initially, you can see link time optimization has a yes on both sides, which would look like parity, but I still want to talk a little bit more about it. And then the rest of these I'm going to go through and sort of describe the state of where things are. So to flash back to the slide from last year, I didn't talk about the stack vector guard location last year, but if we see, the progress between slides, there is mostly just the stack utilization probing, caller save register wiping, and almost everything else is virtually identical to last year. So there's not too much to talk about as far as what's changed, but I did try to flesh out links into discussions. So there's actually something here. So what I want to talk about link time optimization. This works in both compilers, and the reason I have any interest in it is for providing access to control flow integrity, because for the logic that has to happen for CFI, you kind of need everything in one place. So LTO gets us that. A lot of work is needed to change the hat I wear most of the time is from a kernel perspective, but I am going to talk about user space things later here. But on the kernel side, it is a lot of change to the build tooling of the kernel to support LTO, because there are a lot of assumptions made during the build that your intermediate files are actually, are elf.o object files. And in the LTO case, that's not true. So a lot of changes need to happen there. There's needs a Whopper mode, yes, as in all of the memory and all of the time. So this work has been done. Sammy Tolman has been maintaining this and trying to get it upstream, but it's only from the perspective of Clang. Like, I think a lot of stuff is going to turn out to be fixed for the GCC case as well. But I'm not aware of anyone who's actually stepped up to look at this from the perspective of making LTO work with GCC as well. I think. So,
Case, did you see Ian's presentation on Tuesday?
I guess not.
Okay. Yeah. So I think Ian Bierman at Microsoft works on their GNU Toolchain team, and they were talking about how they shipped LTO and PGO in a downstream kernel built with GCC. So I reached out to him and said, hey, let's follow up and try to collaborate on getting build system support upstream. That kind of works.
Yeah.
Works for everyone.
Well, cool. Yeah, I'd love to see this. I have another case in here of I've seen no public work on a thing, but I know it's happening. So this might be another one of those. But anyway, I'd love to see someone who's interested in GCC and LTO actually engage with Sammy's series and see if it's sufficient or if there's more things that are needed.
Yeah, I think Ian claimed they only needed one patch to the kernel, but I'm curious if it was a massive patch because Sammy has lots of patches to the build system. So it's very hard for me to imagine one patch to get it to work.
Well, and I think it may also depend what their config looks like. What does their build config look like and what does their runtime look like? Because if they're not using, I don't know, K probes and they're not using
no modules.
The kinds of things Sammy has ended up tripping over is almost endless. There is a lot of stuff that needs to get fixed. Let's see. Okay, so moving on to stack utilization probing. So this is the stack clash protection. GCC, as far as I can tell, has this sort of in an architecture independent way implemented, and Clang pretty recently just got x86 supported, but the other architectures are still needed.
On the GCC side, we still need to handle overflows in the size computation. And in the alignment treatment, that's still missing.
In allocate?
Yeah, if you need to allocate the pointer and that can overflow. Then you have that gap. And for VLAs, you have the multiplication that can overflow.
Okay.
And you really need the architecture support even in GCC. The generic support is at the level of fstack check, and we know that is not entirely transparent and breaks some things.
All right. Yeah. Okay. Good to know. We'll add, if someone can add that to notes, that would be great. I see in chat, Josh says System Z and Power both have probes as well. Cool. Good. It was, I had some trouble extracting whether or not it existed, but I think that was my fault with it being a late hour. But anyway, further architecture support is needed there, and it sounds like that might be true on both sides. So this is another one I didn't talk about last year, is the stack protector guard location. So on x86, the stack canary used for the stack protector is stored in thread local storage, which is defined as being somewhere in the GS register, if I remember correctly. But that's x86 specific. Until recently, all of the other canaries were basically just being stored in a global variable, which meant that the canary was a per boot global value for all threads. So if you could expose it in, say, one thread you have much more control over, you would be able to, and you had an overwrite available in something you had less control over, it was pretty straightforward to overwrite stack canaries. ARM64 supports now specifying a system register instead of a global, and you can specify the register and the offset and all these things. RISC-V support has been proposed, and this is needed in Clang. Reserved ABI and TCP. I've always heard it described as thread local storage, but okay. Anyway, so getting this in Clang would be nice, and expanding this in GCC to be available in the architectures would be great. And it looks like that's sort of happening. Doesn't look like anyone is interested in having this happen for ARM32. The kernel has a plugin to do this, a GCC plugin for ARM32 to sort of do it by hand, but it didn't look like there was much interest in having it land upstream. Let's see. So Spectre v1 mitigation. This is a relatively expensive mitigation that's in Clang, but in theory does work. It's lower performance than using LFence everywhere. But I can't find any reference to GCC wanting this. And frankly, I had a hard time finding anyone actually using this option in Clang, like in software that was built with Clang. So I'm not sure how much drive there is for having this. It is certainly an interesting idea, and it appears to be the way forward for Spectre v1, because doing it all by hand is not going to be great. To that end, there is a function attribute for enabling speculative load hardening, which on the kernel side might be interesting because it could be used across entry points and some other places where it's a little bit more sensitive. So I'm curious to see its use, but it's unclear to me if there's much interest in making that happen. Trying to read stuff in the chat as well. Next. So this one is under discussion. So zeroing the color state registers on function return. So again, I looked at this some time ago as far as performance impact, and it was negligible since register self-XORing was super pipelined. And it appears to be a relatively strong defense against ROP gadgets, or rather, it means sort of the innate ROP gadgets that are available at function exit suddenly become significantly less useful because the callers say, a whole bunch of registers keep getting zeroed. There's a paper on this that's linked from the issue. I would really like a little bit more research to look at this, because there's sort of been pushback both on the GCC side and on the Clang side about measuring the utility of this. I think that's certainly a valid criticism, but it's shown to clearly frustrate things, and if it comes at no cost and makes an attack more expensive, this is an obvious win to me. So I still would like to see it as it is fundamentally a defensive depth. Maybe there are still other gadgets that can be used in an attack, but if the choice is from 1,000 gadgets to 10, suddenly that's much more narrow, and not all bugs are created equally, and maybe some of those gadgets aren't reachable given the way a bug manifests itself. So I think there's utility in having this. So Nick, yes, Bill is working on this for LVM. That's why that's linked here from the slide. There's still pushback there. And I see, the person working on this in GCC is still looking at performance data. I'll be curious to see it. So one of the thoughts I had on this is there are a couple of automatic sort of ROP gadget building finding tools, and just do a raw analysis. Like, here's the Linux kernel. How many gadgets do we have with this? How many gadgets do we have without it? And sort of, get something that might look would actually give us a better number than making this entirely theoretical. But anyway, these are both sort of in progress, which is nice. And then the glorious stack variable auto initialization. So right now, the kernel has this as a GCC plugin. Clang has implemented this as a pattern init, and also as a zero init, but there's a lot of sort of noise around the zero init version of this because it's viewed as a language fork. That suddenly all stack variables are zero if you don't explicitly initialize them. There's a ton of arguments in various directions, but what it really boils down to is at a practical level, this is what's wanted. Linus has expressly said he wants zeroing as a dependable feature of stack variables. And from a pragmatic perspective, this is being done on Android, Chrome OS, Apple's kernel, and even through Visual C++, a similar option, Windows kernel is doing it by default.
No. Keith, I did some recent experimentation, and there seems to be some of this in GCC on by default. Happened to do this in investigating some Clang bugs that didn't manifest on GCC, and it turned out that GCC they didn't manifest on GCC because GCC was initializing to zero. Whether or not it is, as complete as trivial AutoVar init, I don't know.
Right. So I've found that this mostly tends to be accidental rather than intentional. So it's not something you can truly depend on. I added it's somewhat large, but there are other patterns that were identified recently that are not present. I added a test in the kernel that sort of exercises all of the variations on, are we doing a no initialization, partial static initialization, full static initialization, with and without padding, padding in the middle, padding at the end, like trying all of these combinations to eliminate the sort of accidental zeroing cases, because there are so many different ways that initialization gets done by the compiler. And yes, right now there's a whole bunch of cases that without a plugin, without any extra options, they appear to be safe. But again, that is by accident, which is nice for those cases, but in the cases where it doesn't happen, there's kind of a problem.
At what level is this? Is it at the language level, or is it just we clear the stack?
There's an implementation question. The goal is that the stack memory always has initialized values. So if anything is going to be using it or near it, so all the padding, like a structure covers an entire range of memory, the entire range should be initialized.
Okay, so it's not that if a variable isn't used, then it doesn't matter whether it's initialized or not. Yeah. It must be.
And the question for Florian, do you still need to clear padding? Yes, absolutely. Padding is central to this, because that's one of the major places that things get leaked. Is that open padding that doesn't get touched in sort of the unlucky situation where you're not just doing copy out of read-only memory to initialize it, or if anyway, there's so many different ways right now the compiler implements sort of an object copy or initializations. But the idea is that you have a single flag where you say, now, dependably, padding is zeroed, everything is going to be zeroed going in to this. So it's definitely desired, and my understanding is there's some discussion about implementing this within the GCC universe, but I still haven't found any public references to it. There's notes on packet receive, performance, impact. I don't doubt it. I'm sure there are situations. There are some cases where we want to opt out of this initialization, but my goal is to have the feature available, and to quote where I heard it first from Jan Horn was to basically downgrade a security vulnerability to a performance problem and then solve the performance problem.
Yeah, I kind of wish that the C standard had it that the stack variables were initialized to 0 by default, and you could say, don't initialize this for performance reasons. That would
Right,
be nice.
exactly. And like the objections about it being a language fork, like I'm okay with that. I want that. I want determinism is the issue. Like it's one way or the other. I don't really care, but determinism is what's critical.
I stopped looking at this in 2014 because at the time we actually hit the issue in the socket receive path and with the socket address handling, and that was a major source of data leaks. So you wouldn't want to opt out at that point, and there was a significant performance hit for small packet receiving.
Right, and like again, I think converting from security problem to performance problem is the way to go. I agree with you on that observation. See, I'm just catching up on. Alexander is commenting on the fact that there are sanitizers available. Yes, that's true. Please turn on your sanitizers. I'll get to that. How much time do I have? So structure layout randomization is a delightfully insane feature. We've got it as a kernel plugin. There's a Clang support proposed, but sort of stalled, needing more work. It's really fun for paranoid builds. There are not a lot of people using this, but the folks that do use it are extremely interested in having it. They're highly motivated to have significant build diversity. And I found at least one phone vendor that before the change to Clang in Android was using this for their images. Nick is asking if there's anything kernel specific about randomized layout. Yes, I'm going to say the short version is yes. The long version is much longer, but it's not a lot specific in the kernel, which is why it could go into Clang. There are various considerations. So sanitizer. So signed overflow protection. I, much like the reference counting BOF that was just before this, I really would like to just solve the overflows as a class. I need to be able to describe our types and say, I expect this to overflow or I do not expect this to overflow. Anyway, the first step there is getting these sanitizers. So GCC and Clang both have this and it works. There are, however, some kind of weird behavioral issues with how it relates to the kernel and the F no strict overflow, which sort of allows wrapping in some situations, which means the signed integer overflow sanitizer is not guaranteed to correctly instrument all of the arithmetic places where there is a signed overflow happening, which is a little frustrating. So nailing that down and sort of figuring out the differences between GCC and Clang is the next step there. And then sort of API-wise right now with the sanitizer, this is part of the UBSAN, the Undefined Behavior Sanitizer. And right now it effectively operates in two modes, which is just die, kill the program, or warn about the problem, but then merrily continue with the whatever the wrapped overflowed value actually was. And it would be lovely to be able to declare a saturation value, which would sort of mimic what's happening with the kernel's reference counter type, which will saturate to int min divided by 2, so it's in the middle of the negative space. Anyway. So that's sort of an expansion of a feature request on the signed overflow protection. Which gets me to, I keep hitting page up and down. So unsigned overflow detection. This exists in Clang. It does not exist in GCC, and it isn't technically an undefined behavior, but it can be sort of an unexpected condition. Which usually means it's exploitable in some fashion. Either it's a robustness issue because we get bugs, or it actually becomes a security issue. That said, there are, of course, all kinds of places where the expectation is to wrap around. So separating those types in the kernel is something that I'm interested in doing. And technically, even having support for one compiler on this is sufficient, because the type separation will occur regardless of which compiler catches it. But it would be nice if everyone who built their kernel, regardless of compiler, would get the appropriate instrumentation. It has similar caveats to the signed overflow and similar needs. Nick is asking about layout randomization. So to manually enable structure layout randomization is a structure attribute. There is an additional mode that specifies an auto detection way, which is to say, if a structure contains only function pointers, it should be randomized also, unless it has the reverse attribute applied, which is to not randomize those and that tends to be things like cross software boundaries, like Zen, virtualization tables, or things shared with firmware, stuff like that. And I'm running out of slides. Let's see. So backward edge CFI, protecting returns to sort of stomp out return-oriented programming. Obviously, this is almost always better in hardware. On x86 will have CET, which is a CPU feature bit, and it's implicit. There's no compiler support needed, so that'll be sort of done. On ARM64, there's the pack instructions. This is supported by both GCC and Clang, and Clang added the attribute support recently. So that exists now to both turn that on and off on a per function basis. Doing this sort of in an emulated fashion, use like a shadow stack tends to be the most well understood version of doing backward edge CFI. x86 doesn't appear to have a viable version of this. There was one in Clang for a while, but it was both slow and had race conditions. So it was effectively just removed. And then on ARM64, there is this in Clang, but it does not look like anything exists for shadow stack style things in GCC that I've found. On the other direction, forward edge for handling indirect calls, function pointers saved in the heap, function pointers saved on the stack. Hardware support on here is unfortunately extremely coarse-grained. It basically just limits to an expected entry point, which is to say, instead of being able to jump to any byte in the text function, in the kernel text, you can just jump to any function you want, which is like, that's sort of already what attackers are doing. They're not really interested in arbitrary bytes. They're interested in elevating credentials, and that's going to be done through function calls. So coverage there isn't fantastic. However, if it's in hardware, it's relatively free, so it's good to actually mark it up, because it does narrow the scope of what can be jumped to. Again, the hardware side is supported by both. On the software side, getting really fine grain with the per function prototype is what's happening in Android right now. This is again work from Sami Tolvanen, which implements support, sort of the runtime support of this from Clang's CFI. And I really, really, really want this in GCC. I mean, it's nice that we're getting a bunch of sort of prototype cleanups going into the kernel, which is fine and all, but it doesn't actually provide anyone with any protection if you're building with GCC on the kernel. Getting this fine, like there is not on the horizon fine-grained hardware support for forward edge CFI, and this is one of the strongest sort of post bugs, so exploit technique eliminations that we've got right now. And getting parity on this in GCC would be wonderful. But I've seen 0 people talking about how to get this implemented in GCC. And as far as I can see, the major prerequisite was LTO, and that exists. So it would be lovely to see progress here. As far as the virtual table protections, I have no idea if anyone's actually using it. So that was an older thing, and it's C++ only, but I thought I'd at least mention it here since it is technically an indirect call protection mechanism. And I think that's yeah.
If we have static call, can't we just replace all of our indirect calls in the kernel?
Sure. If we can, why not? We'll see, but we would still need, like, I am curious to see how the sort of stored function pointers in heap end up getting manifested in that one, like the various callbacks and other things. It seems like it solves a subset of the indirect, like stored indirect call stuff. You are being sarcastic. Okay.
Yeah, I'm about to say the overhead of changing a static call is quite high. It's only for things that are, you always call this until a user says otherwise. Then you can use static call.
Yeah, and it's actually, it is nice. Like it does provide, it really does close some of the areas. I actually think that it's a good example of turning a security problem into a performance problem. And not that static calls aren't performant, but in fact they are performant. So we have a lot of places where we are effectively sort of doing already a kind of a manual CFI in the kernel, where we look up in a table which function do I want, as opposed to storing the actual function pointer. And that's kind of a CFI. And those get replaced by static calls, and suddenly the overhead from the reptilians and the indirect calling and any looking up CFI tables and all that stuff goes away. So suddenly we actually solve that performance problem. So yeah, I'm really looking forward to the static call stuff landing. There's a series for the LSM to remove sort of the LSM callback overhead that grew a bit once LSM stacking went in with the static calls, and that would be lovely. And yes, to refer to the wrap that PAX has, yeah, it's also a forward edge CFI, but it's not publicly developed, and it depends on memory, text being readable. So it is not compatible with execute-only memory. Not that we necessarily have execute-only memory yet, but it's certainly on the horizon. Execute-only memory plus fine-grained KSLR really gets you a strong defense as far as raw like gadget discovery. Anyway, that's the end of my slides. I think I'm still a couple minutes early, but that's it. Anything people want to talk about, please pop up or say things or type things. I'll try to keep up with chat.
So out of this list case, what if you only had money to put towards implementing one, what's the most important one right now that we need?
Well, first I have to figure out which hat I want to wear to answer that question. I think ecosystem-wise, I think forward edge CFI in GCC is by far the most important. Being able to have that on every distro, as well as how we're getting it on phones right now, I think would have a huge impact on sort of the difficulty, the general cost to building exploits. A lot of the rest are sort of they're more around specific bug classes, like the overflows and making certain types of bugs harder to get a foothold on. But I feel like getting forwards, I mean, backward would be nice, but it looks like that's mostly going to be hardware. Getting the forward edge CFI implemented universally for Linux would, I mean, it's not a perfect solution. There's a lot of detractors that point out that, you know, if CFI catches the exploit, there's still a bug that was being used to do it. So it's possible that there will be more ways to get around it.
And on the LLVM, sorry, go ahead.
Oh, I was going to say I sort of view it as kind of giving people some breathing room, right? Like if we get forward edge CFI landed, then maybe there's enough space to start fixing bugs, like bug classes, instead of the individual bugs that have been plaguing us that lead to, you know, indirect call exposures and things like that.
And on the LLVM side, what's the first place we should focus efforts, given limited resources? What would be the most valuable win for us to focus on?
So I think the sort of head-slapping realization I had yesterday while finishing up these slides was realizing the stack protector guard location isn't supported at all in Clang. It's like, like we just gained per thread canaries, but not on any of the phones. Like it's just absent. It is just how it was a couple years ago. So that one really stood out to me as being like, that needs to get fixed quickly. After that, I think, I don't know, getting caller saved register wiping is interesting, but it's a lot less interesting than the stack protector guard location.
Cool, thanks.
That's today's opinion. How good is security parity across architectures? That requires a lot more research than I have done at this point. I've sort of mostly been focusing on the architectures that have the apparent largest number of people using them. So I've mostly focused on x86 64 and ARM64, while also trying to pay attention to what's happening in S390, PowerPC, RISC-V, ARM32, and x86-32. I have been wanting to generate sort of a three-dimensional map of like feature to compiler to architecture. Like it gets complex, but there is it's not great in the things outside of x86 and ARM64. Things fall off rapidly. That said, I would say PowerPC continues to make a lot of good stuff. I feel like RISC-V is coming along nicely, but they just got a lot of work to do. Like they're a new architecture. They're filling in the gaps as they go. And for S390, I always feel like by the time I go look at S390, they have sent a patch for it 2 weeks earlier. So I don't know. It's an interesting game where the gaps are, and even this, like I forgot that the stack protector guard location was just not implemented in Clang. Like, whoops! We really do need to have that answered better.
Yeah, I'm just going to throw out, this is a little brainstorming here. I was just thinking about, Nick mentioned about, it would be great if we had, got rid of function pointers. So say like the VFS has a lot of function. I mean, you get a table, that's probably the biggest common thing of setting up function pointers and set. And it would be great if we could set that to static calls. Now, static call is usually just for the actual location and code. So since you open function call, depending on which file system you have loaded, it's going to call a different open function. But that said, there could possibly be something like there's not people don't usually load that many file systems on a machine. We could possibly, I don't know, this is just going to throw this out. You could possibly set every location to be a jump table. So basically, it'll automatically jump to the first location, read something variable, do a branch to the index that jumps to a table. So every single open call will actually be registered. Open will call and we dynamically create a jump table. Do this,
yeah, and,
or,
and that's, I mean, it's basically what I would describe as like manual CFI, because what you describe is literally what the compiler does for building the CFI tables. Like it builds a jump table, it validates the index, and it does that. It does it based on the only information it has available for the greatest sort of uniqueness, to have the fewest number of valid call sites, and that's looking at the function prototype. So for many cases, you actually get the same mapping. Right, like for the function prototypes, you're going to have the struct of, you know, the whatever VFS handle or whatever is involved in the open. So all those prototypes look the same. There are kind of cases where two prototypes look the same though. So adding this kind of knowledge would be interesting, because you might end up with even finer grained version of it. But yeah, absolutely, I think that's a good idea. Right now, it's sort of focusing on the big hammer approach, which is letting the compiler figure that out.
Case, when you mentioned execute only memory in the kernel, is there anything we can do with like mapping, like setting permissions on, like trying to move any of these function pointer tables into memory that we can like maybe set it read only after a certain point, or execute only, whatever we need kind of thing? Like I'm interested in trying to protect blocks of function pointers as well.
Right. A lot of that is in the like read-only after init work that happened, and like some of that exists. It would be nice to have sort of data at rest not writable. There are a lot of approaches. There have been a lot of ideas there. It's more of a sort of a little bit off topic in this, but yes, the version is. It would be nice. There's not a clear path towards it right now.
Peter Zylstra has been pushing strongly on this. All data within the kernel is either writable or executable, and they're mutually exclusive.
Sure, but I can still write a function pointer to the heap, and then later I read it back and I jump to it, and then you're
but the heap would be not executable.
Yes, but I can jump to any function in the kernel.
Oh, so you say you have to jump to, so basically jump to a function. Okay.
Yeah, and that's right now we already have write not execute. That exists as a thing. The main focus lately has been on making sure that can't be violated by modules, enforcing that can never happen, because prior when loading a module, it was allowable to still be writable and executable. All through the kernel though, in the main text, that was disallowed, and we have a boot time verifier that'll actually scan the entire VMA, like all the VMAs of the kernel at boot time, and find any places where that accidentally went wrong. It wasn't as tightly controlled on modules, even though they were, built correctly in most cases. Anyway, I think I have minutes remaining. 25 after. So I have 3 minutes left.
About the RISC-V protected guard patches, I think the GCC seems approved patches, and the kernels have a proposed one, but not be tested. Maybe I will send the patch with the tested by when the GCC released next time. Oh
yeah, I think it's fine to as long as the feature names are correct, we can just land it in the kernel because it'll detect it once the GCC has it. So yeah, that'd be great. We'll have a sample of it.
Okay, got it.
Regarding forward H CFI, did you have a chance to look at the PAX method, which uses function signature check verification before call, and each target function has a hash of the signature right before the function start?
Right. Yeah, I'd mentioned that earlier when it came up on chat, which is they have, instead of their implementation of forward edge CFI doesn't use jump tables. It uses sort of built-in hash checks, but the same, at least in the version that was last public, the same hash, or the same granularity. In other words, the function prototype granularity. The two issues that I sort of point out is that one, it's not openly developed, and that's not what's in any of our compilers right now. Like from with my kernel hat on, I can only use what's in the compilers, and the implementation depends on the kernel text being readable to actually read out those hashes. So it's not compatible with execute-only memory that would not be readable. It would be only executable. And the goal, sort of planning-wise, is to have the text be unreadable. Ultimately, we're still sort of waiting on hardware support.
Is it hashing the function? Oh, sorry. Go ahead.
You first.
Nick goes
right now.
You're muted now. Okay.
Sorry, I got a lag in the UI. Yeah, so isn't hashing the function signatures how mod versions works to protect, but it's only a build time check for kernel modules, right? Is like trying to enforce that build time that the ABI or the function signatures appears to match between caller and callee. And
yeah, I mean, I think
my concern there is like, well, where's the runtime check or enforcement on that? Is, I want both a build time and a runtime check.
Right. I mean, the hashing that wrap does is sort of like it's just a hash based on the prototype, and the effective hashing that is going on with Clang is sort of the combination of jump table location and index. But it turns out to be the same, which is to say a unique combination to describe a specific type, a specific bucketized set of reachable functions. And it's still a heuristic is the main thing, which is why, to Stephen's point, having this even more fine grain, if we can declare it within the program, within the kernel, we might be able to break those buckets down into even smaller buckets. Because, to go with another observation from Jan Horn is like, so if you have a stored open, so what? I can call any open I want. What if I call the open for dev-pid mem? Right? So, but again, my point is about narrowing the scope of an attack. Right now, an attacker can call anything. If you can only call open, okay, fine. That narrows the possibility of what's possible. I think I'm out of time and over time. So, thank you. Bye-bye.
Thank you, Kish. Okay, we have 7 minutes until the next presentation.
Can you hear me okay?
Yes.
Good.
Okay, well, you can take presenter yourself, right?
I think so.
Otherwise, okay, let me do it. Oh no. Yeah. So now you are the presenter.
Got it. Let me see. Okay, so while we're waiting, we can maybe start the poll already.
Okay, 35 here. I think we can start, Florian.
Okay, then let's start.
Thanks.
I'm going to talk about glibc and system call wrappers for Linux. I shouldn't have gone back with the slide. Now I have to wait until it goes forward again. Okay, so let's go right in. here is an example of a system call wrapper, how it's implemented in glibc. It's for the lseek function, which changes the pointer of a file descriptor. And as you can see, there's really not that much code. So we just load the system call number. That's 8. Perform the syscall instruction, and then comes some magic checking that basically sees if it's an error or not, using in-band signaling and a magic limit that tells the regular return values from the error case. And at the label here below, that's the error case, where we basically write the error code to the thread local storage for the error variable. And if we don't have an error case, we just return. So it's basically like 5 instructions or something like that. So why do we even need a library function for that? We could do that inline all over the place. And we actually have something like that. It's not actually an inline expansion. It's a generic system call function called syscall. So why don't we use that all the time? The problem there is that you have to remember to use the correct types. So you actually have to cast the 0 to off64T on some architectures in order to get not an int, but a long. And then we have quite a bit of divergence in terms of the system calls. For lseek, there's actually _llseek that has split arguments for the offset. Peter, can you please mute? Thank you. And returns the offset via a pointer, and obviously not everybody needs to know these differences. So that's one reason why I have wrappers. And since the current policy is to use the latest version of every system call for new architectures, that happens quite a lot, actually. So we have it for open, which went to OpenAT, and which is going to move to OpenAT 2 at one point, I suppose. And for futex, we now have futex times 64. And given the architecture variants we have in glibc, we have a bit of a preprocessor conditional there that uses the complicated non-64-bit system call if we have to. And for the 64-bit case, we go straight to the inline syscall call macro here. And the inline syscall call macro knows about the kernel calling convention. It has type inspection for some architectures so that integer arguments are correctly sign extended or 0 extended as necessary, same for pointer arguments. And the inline system call, the inline syscall call macro also handles the error update transparently. And because the arguments for the user space calling convention, the function call sequence and the kernel call sequence match so closely on x86-64, we got this extremely brief assembly code as before. So that's not actually handwritten. It falls out of this C function definition. So GCC does a pretty good job there. I say without symbol management here, this is if the system call is used within glibc itself, you have to go through some steps to make sure that you comply with static link namespace requirements and also avoid relocation dependencies, so that you don't get any runtime allocations you don't want. But for new system calls, you don't have to do that because there are no users within glibc yet. So what are the implementation options for glibc? As we have seen, we can use inline syscall call. That's a macro that basically does everything, including setting errno for errors. We also have internal syscall call, which is similar but does everything until the errno update. So you have to check manually for the error case and handle that separately. And for regularly structured system call that has the same signature across all architectures, we can also auto-generate assembler implementations if we want. And there's a text file basically that describes the type signature, not in C, but in a fairly abstracted way. And then there's a bunch of shell scripts that generate the assembler code. You can also write manual assembler implementations if you want, but usually for almost all system calls, if you need that, you must have done something wrong when designing a system call. You really shouldn't be needing that. Exceptions are things like vfork or certain types of clone, because of the way the stack is clobbered by the other process. So you have to make sure that you don't write you have to capture the return address temporarily in a register. But that's probably the only exception you're ever going to need, unless you're doing something terribly wrong. So what's the process for adding system call wrappers? Sorry, I forgot to stop the poll. Where can I do that? The published polling result. The question was, A was who is a kernel developer, B is who works on user space toolchain, and C was who is working on something else. So we have a nice distribution, a pretty even split actually between kernel developers and toolchain developers, which is nice. So the question is, where can I, Jose, do you know how to stop the poll from appearing?
No. Where is it?
There should be a garbage can to the right of you.
Thank you. So, sorry about that. So, what can you do if you want to contribute a system call wrapper to glibc? So, the first roadblock is actually copyright assignment, because you probably won't stay below the 15-line triviality limit that we've been told is the most we can accept. And the good news is, despite the disturbances we have seen in the flow of goods and services around the globe this year, this doesn't seem to have impacted the FSF copyright assignment procedures. So they still process assignments from pretty much anyone, even though they are based in the US. So, and the process has been, I think for most jurisdictions, it's now fully digital. So if you are fine with assigning your copyright, you can actually do that in a pretty painless fashion today. So then the next steps are, you need to determine the header file where you want to store the prototype for the user space, the header file which goes in user include. And then sort of related to that is the API scope. So we have like 3 levels in glibc. One is the standard level, so C or POSIX. Then there's the GNU level, which is sort of the GNU API with extensions, and it's currently shared by Linux and GNU Herd. And at the end of the spectrum is the Linux specific system call or function. And then you need to decide, should it be a cancellation point? The answer to that is no. So cancellation point means that the thread unwinds its stack if it gets canceled via pthread cancel. And that's a very unusual, currently it's a very unusual thing to do. Some of the IO functions do that. What's it? Some of the IO functions do that, but it isn't even implemented for all system calls that can block indefinitely. So if you're on NFS, stat can block, but it's not a cancellation point, so it's not really useful. So for new system calls, probably not necessary to do that. Then you need to find the right place in the source tree. There's a subdirectory called MISC where these things can go for if it's at the GNU API level, or it probably goes into systems, Unix, sysv, Linux, where all the Linux stuff resides that's architecture independent. And then you have to update the versions file, which defines the user visible ABI, so what gets exported from the compiled shared object. And you also need to update the architecture ABI list, which we use internally during the build for verification that we export exactly the symbols we want. For a new system call, we would also like to see a minimal test case so that the error reporting works and that basically all the arguments are forwarded into the kernel and that the types work so that you can actually compile user space code using the header that the prototype you have written into the header. Doesn't have to be anything fancy, but just a minimal test case. It's not always possible to write that for privileged or highly advanced system calls that need some sort of infrastructure library support. We also need an update to the glibc manual, which is GFDL licensed with invariant sections, which means that a lot of people never go to see it. Debian doesn't ship it. So Debian and its downstreams don't have it. But still, we need to document something there. It can be for complex APIs, it probably can be a link to external documentation. We did that recently during the RSEC work, so that's already a possibility. And we also need to update the news file. I put that in there because all ABI changes should be announced there, and it's something that is easily forgotten. The good news is you don't have to write changelog entries anymore. So we got rid of that requirement. You just need a decent commit message. So I would have liked to include some sort of tutorial here, but it turns out that every system call is a little bit different. Still, there are clear patterns emerging, and usually you can look at a similar system call and see how its patch was written. But yeah, there's if you are changing. If you're adding a fork between the GNU version of a header or the GNU herd version of a header and the Linux version of a header, then that needs special code that's unusual. And also we have a backlog in terms of what needs to be documenting in the manual. So we're working on clearing that up, and that should also simplify adding new system calls. In general, I'm trying to make sure that a first-time contributor doesn't have to follow all the obscure rules about GNU style coding with the braces placement and two-space indentation and stuff like that. I think the first patch you submit should be basically get a pass on that, and we just clean that up for you if you don't want to work on that, so that it matches the style guidelines. Basically, if you can make the copyright assignment step, then I think you're basically pretty much good to go. And we try to make sure that, at least for first-time contributors, we are not too nitpicky about the style rules. So the overall state is that the good news is that we have consensus that we can add wrappers for basically everything that the kernel supports, even if it's very, very much Linux specific. Exceptions are obsolete system calls or system calls that break core library glibc or user space invariants. So we're probably not going to add a system call that allows you to change the thread pointer that glibc uses. Because if you do that, then you can't, at present, you can't call any other glibc function anymore. And so it's not, that would be an example where the core invariant is broken. So in order to underscore this point, we finally added a get-hit system call wrapper in glibc 230. That's about 1 year ago, after a discussion that spanned a decade or more than a decade. And I think it shows that we are basically over the bump, and we are basically open for business at this point. That doesn't mean that we have any sort of parity with the kernel at this point. There's still a long backlog, and it's also problematic that we haven't manual documentation for some core concepts that are relevant to many of the new system calls, like the open-add relative the path-name-based, the file descriptor-based path-name resolution is currently not documented at all in the manual. So if you want to document a new system call that does that, you basically would have to invent that from scratch, and we're working on these things and trying to get more of that documented. And there are downsides of adding wrappers, and so far we sort of ignore them. And what are the downsides? So the major problem, I think, is that each time we add a wrapper to glibc, we have to add a new symbol. So it's a new function. And the policy as it is now is that we can only do that at a release boundary. And since glibc releases happen twice a year, you face a waiting time of 6 months until you can actually use that in new applications on brand new current distributions. On the other hand, distributions do not backport these wrappers. So if you try to run an application that uses get-hit, then you get an error message if you try to run that on glibc 228, for instance, because it was added in 230, and if the distribution has 228 as the version, then it just can't run the code. There's so it's different from backporting system calls that some distributions do that very aggressively and backport tons of new system calls. For Fedora and Red Hat Enterprise Linux, for example, we just don't do that for glibc system call wrappers. And one aspect there is that our dependency generation depends on these symbol versions. So we would have to backport the entire glibc 230 symbol set before we can add one tiny system call wrapper. So in practice, this means you have 3 years waiting time until you can actually use that in applications, maybe more. And each time we add a wrapper to glibc, we have this temptation to add a user space emulation. And every time we do it, we kind of regret it afterwards, because the kernel then goes off in a different direction we didn't anticipate originally, and then we have to maintain our and we have to adjust the system call emulation in user space to match the kernel behavior. So I kind of fall into that trap with copy file range recently, and what we did there, we actually backed out the emulation again, and you get own enosis if the kernel doesn't implement it. So the exception I can see to that rule is that if you have a flagless system call and that does the same thing, and the caller passes a 0 flag, then you might want to call this flagless system call. There's so for nanosleep and clock nanosleep, there might be I'm not entirely sure if there's a difference there, but in general, this seems to be safe. Now, the downside is that once you adopt new system calls, browsers stop working if it gets actually used by core runtime libraries. And systemd spawn doesn't really handle new system calls well. It fails them with eperm instead of enosis. And since eperm is a valid response for many system calls, you can't really do fallback safely in that case. And one concern is that once you add wrappers to glibc, more people might want to use these system calls, and things break more quickly than they do today. So this is mostly relevant to clone and clone 3. So a glibc system call wrapper cannot be used in all contexts, where you can call a system call directly using the syscall instruction. The main reasons are that if the system call fails, we need to report the error and use error for that. Error is a TLS variable, and that depends on the thread control block. And after clone 3 or vfork or clone, you may not have a valid thread control block. And we kind of ignore this at this point, but if you do very fancy things, then stuff tends to break in pretty horrible ways. Even if you start building glibc with stack protector all, then you get stack protector instrumentation for the system call wrappers. And at that point, you also have a TCP dependency. So depending on what you're doing with clone, you might actually hit problems in this area. And some glibc functions aren't really system call wrappers, like setuid looks like a system call, but is not in glibc. We have to call setuid on all threads of the process, because the kernel system call only changes the current thread user ID, and POSIX mandates that you have to change the user ID of all threads in the process. And that doesn't really work after clone if you use the wrong clone flags. That is, it depends on the TCP, and the current thread identity isn't really reflected in the rest of the process. And there's POSIX cancellation handling, which might trigger unwinding if if you hit a cancellation point and after clone, that's going to be very bad. So there's also lazy binding. If you don't build with bind now, then and the function hasn't been called before, you call into the dynamic loader transparently behind your back, and that's not really prepared to deal with a situation where you're in a restricted execution environment like after clone. And this is actually news, unfortunately, to many user space programmers. And it's related to asynchronous signal safety and these matters. And syscall, the syscall generic wrapper function shares some of the problems. So it also has it uses error for error reporting. And therefore, it also needs a TCB. So what we can do about this, maybe we need new kinds of wrappers like a different function with a different naming convention that uses inline error reporting like the kernel and doesn't use error, and it's a statically linked hidden function symbol so that you don't have to call a dynamic loader when you use it. The wrappers have to be built in glibc that have to be built in a specific way so that there's no TCP dependency at all, and there's no cancellation point. And so that with all these things, you can actually make sure that the system call wrapper is usable after clone. And if you do that, maybe we can provide more useful functionality in conjunction with clone 3 going forward, and don't have to add everything you might want to do to the action lists that POSIX spawn implements. So POSIX spawn is the POSIX answer to this problem that you can't do much of the things you want to do after fork. Basically, you record an action list and the glibc implementation then. Nick, you want to ask something?
Just to note that when I was adding stack to support the glibc, I was of two minds whether I should whether syscall wrappers should all be inhibit stack protector or not, because when you set it, we're not really what's going to smash the stack. It would only be the kernel or a bug in the syscall wrapper itself. I would not be averse to just saying all the syscall wrappers should be inhibit stack protector, which would fix this problem. I don't think that would expand the over much.
So what I think both stack protector, the historic stack protector option, and stack protector all should probably go away. And if you use stack protector strong, because there are no except if you have some sort of emulation or fallback and coupling around data, if you don't have local addressable variables on the system call wrappers, then they don't get stack protector instrumentation. But you're right, system call wrappers usually do not need stack protector instrumentation. We have one exception for MIPS where we have to have emulation for getDense64, and this is this huge function with buffer management. That's actually a place here where you would want stack protector instrumentation.
I would say we want it in the manually written ones, but in the auto-generated ones and the ones that just call the inline, there's no point.
Yeah, but the counter argument to that is the automatically written ones are currently assembly language. They don't have any debugging information at all that's useful. So you can't see the arguments if you hit stop the process at that point. So that's kind of a bit an annoyance there. So probably that's going to be fixed by writing automatically generated system call wrappers in C instead of assembly, and not instrument those.
Just
I
to
don't know.
note that Siga Bossencool asked earlier in the on the GNU Tools track if I could submit a patch which flips the default to the stack protector, so it's strong by default if supported by the compiler, otherwise not strong, otherwise off. It seems like a reasonable thing to do. It was only not default because it seemed too invasive. It's been years, no one's complained. I should probably flip the default.
Yeah, it makes sense. I think we can enable it by default, or at least inherit the compiler default or the.
Oh, that was the plan, basically. You asked the compiler. I do, except for all, which I think you probably should only be on if you're crazy. I have it turned on for my firewall.
Yeah, a stack protector all has a bunch of problems. Okay, so but the point is that if we want to support these restricted in execution environments for clone 3 and the like, we may need different kinds of system call wrappers. And the interesting thing there is because they have to be statically linked, there's no ABI impact, and we can start backporting them pretty widely in order to support application development, even on all the distribution versions of glibc. That's just an idea. I don't know if it's going to happen, but it would mitigate the issue that you have to wait 3 to 4 years until the system call wrapper becomes available in glibc and is in wide use across distributions. Okay, so now I'm starting to speculate about things that the kernel could do to make things easier for us. I mean, you could always write the system call wrapper for us and submit it to glibc at the point where you contribute the kernel patch. But apart from that, what can we do to make this easier? So one thing I'd like to see is no more multiplexes, because they don't really add that much value above syscall, calling the syscall function directly. Some of them don't have type safety. What happened recently with the Time64 work is that you now have to port software to use that new system call, even if they don't use the footex variant that doesn't have any time argument, or that doesn't use the time argument at all, because it's tied into the system call and not the actual argument usage. So the wrapping the multiplexer as the multiplexer in glibc is probably not the right thing to do. So I'm looking more at, for footex, I'm expecting that if we get to that point, we are going to do something similar than what we did for socket call, which was the historic implementation for all the BSD socket API there. We didn't expose socket call, but the actual operations behind socket call had all the different separate functions that you would expect, like bind, accept, get peer name, get sock name, and connect, and all these functions. And maybe we should look at footex in the same way and say, okay, it's basically footex call, and what we have to do is we have to split it up into separate functions with variants, whether you want time waiting operations or not. And
there's also the new proposal for Futex 2, which is not using a multiplexer. So, and I've been wondering what you expect to do about that in glibc. You also mentioned that generally you tend to implement the new syscalls by using the old ones if possible, but I'm not sure if this is possible or if it's a good idea.
it depends on what the final interface will look like, I think. And there's value from doing it in a uniform way, and especially if Futex 2 arrives before we get to writing the Futex wrappers, then maybe there's going to be only one single one user space system call wrapper for that, or set of wrappers.
At least then the applications could move to just calling that.
Exactly, and I don't have to care how it's implemented. Internally in glibc, there's currently a policy that we call the newest version of the system call. So that's based on looking at the kernel implementation, which does that internally. So basically, we think that we go right to the full, most extensive system call, like what the kernel does internally when the older system call is encountered. I think people noticed that in particular when we switched the open system call to open add, because that's that they had to adjust their strace-e filter arguments.
And also all sec computers. For Vutex, the plan is actually to have a separate implementation in the kernel and not have the old Vutex call into the new Vutex 2, because they're just too complicated.
Okay, in that case, I think it's probably best to mirror the split. Otherwise, we might end up with behavioral differences unless the kernel can somehow guarantee that that's not going to happen.
No, I think the feature set, while there will be an overlap, each version will have some things that the other one doesn't have.
Okay, yeah, I think we need to look at what is actually happening there on the kernel side and then reach a decision. The other issue with multiplexers is that if you have a 32-bit variant of a 64-bit architecture, then if you sort of screw it up, it can happen that the kernel API and the user space calling convention do not match. And at that point, you have to do argument translation, in the sense that you have to do sign or zero extension from the 32-bit register to the 64-bit register. We have to do that on x86, 64, x32, the ILP32 variant for the AMD 64 architecture. We can do that in a pretty consistent fashion internally in glibc, but if we want to do it for a multiplexing system call like PR control or syscall itself, we basically have to have a giant switch statement there in glibc and teach it about every variant, and we don't want to do that. And if the it's much more likely that this works reasonably well if there are no multiplexers and we have a system call, one function per actual operation that has the correct argument types. So pointers are pointers, and ints are ints, and unsigned ints or unsigned longs are unsigned longs. And so the other issue that relates to the HJ, do you want to ask something?
Yeah, I want to comment on the PR control for x32. Normally we do not need a special wrapper for syscall. We can share the same auto-generated syscall wrapper for syscall. But for the PR control, it's a special thing is we are using this 64-bit interface. However, the 64-bit interface expects a 64-bit, a pointer to a 64-bit address. 64-bit the address. So that's what the wrapper is. Widely needed wrapper for RPI control. As for the switch table, no, they're not going to be a giant switch table with the very simple switch table. We only need special case for those two variants. Other than that, everything else will be the same.
Yeah, I was with the giant switch table. I was thinking about the syscall function because if currently you can't call read, for instance, safely. I think you can't call it.
Yeah, for the syscall wrapper, it is special case. Yeah. It's even. I can imagine even in some special case, even the 64-bit variant may not be safe to use that directly. But will be, of course, XD2 will be much more often.
And I think the key takeaway is that if you implement a multiplexer and it gets really complicated, and it's type polymorphic in the sense that the function argument types change based on the operation code, then you can can end up in a similar situation, and that's not something we can support on the glibc side readily.
Yeah, that's certainly something we have to consider. Yes, but I'm only talking about the ArcPR control. That's because as you may have noticed, I'm extending the support for shadow stack, and for that particular usage, and if we are careful, both on the glibc side as well as on the kernel side, there should be no problem. Of course, have to be very careful about this.
Yeah.
When we adding the new operations, has to be extremely careful. Otherwise, we will run into issues you point out. But so far, for what I see, the extension we made for shadow stack is safe. But all cases, but I'm only talking about specific cases for our control. We do. The reason I want to avoid the new system call for every operation is the system call number is a kind of scarce resources. So
I'm not sure if that is really the case. I think the problem there in the past was, can go to the next slide. In the past, there was the problem that it was really a lot of work to enable a system call across all architectures. So you got your tentacles into the kernel. At least that's from a non-kernel hacker perspective. That is what I sort of think what happened. And then you basically did the work once, and then you had your small little island you can inhabit and do your work there. And for each operation you just add something locally to your generic system call interface. And maybe that's not needed anymore. What I noticed is that the many more system call the enablement process is much more consistent across architectures at this time. It's not like that it is smeared across like 5 different kernel releases anymore, and that's a good thing. So
I want to go back to scarce resources thing. The reason I'm saying that the way we implement x32 system call, we did it in such a way the range of system call numbers is limited. I do not know how many free unused system call numbers are left, but it's not a big number. I think maybe less than 100. More couple hundred, but definitely it's not a big number. It's a very relatively small number. So I would like to avoid adding new system call just for this particular case. For shadow stack, we're adding 4 or 5 system calls, and I'm trying to avoid that because the system number.
Okay.
Yeah, it's limited.
Yeah, that sounds like, but that sounds like a generic concern. It's an interesting point. Yes, I wasn't aware of that. Okay, so one thing I'd like to mention, I think I'm almost out of time, is that it's really important to have the appropriate types in the function signature. So please use unsigned for flag arguments and are long, and use size t for sizes and not int. So there have been some historic mistakes in this area. And we look at this when we write a system call wrapper in glibc and think, okay, what should we do? I mean, if there's a size, we really want to write size t in the interface. So do we then check against int max before calling into the kernel and return an error directly and stuff like that? So it makes it easier for us if the right types are used. And 64-bit arguments really need to be passed in memory, otherwise you end up with the thing we saw in the beginning with lseek and splitting up 32-bit arguments across two registers, or even more crazy variants for the period system calls we have. Okay, and so probably what helps for user space programmers, not just us in glibc, that's more like what the users get when they finally see what glibc provides in the header files, is that it helps to have some established conventions for extensibility, so that there's some uniformity across different system calls from a programmer perspective. So you see, okay, I need to write the size of the struct argument here, and it's sort of consistent for both system calls, and it's not different for every system call does its own thing. And that is related to the thing that HJ said. The question is how many system calls we can add. And Jose?
No, the time is up.
Ah, okay, yeah. I never saw any of the...
Yeah, well...
There was something with the video.
The thing is that there is no break now that we could abuse. Next talk starts straight away, yeah.
Yeah, sorry, Florian. I was posting the cards. I don't know if people saw them or not.
Yeah, the talk was so good, Elena didn't want to tell you to stop.
It was a good one, yes.
Okay, then thank you for your attention, and I hope you found that useful, and we might get a few new wrappers out of that for glibc.
Thank you, Florian. All right, so next presenter.
Hello.
Hi.
I think we have an issue with the cameras. I don't see you guys. Can anybody see either Jose or Christian?
I can see Jose.
I can see Christian.
So it's my fault. Ignore me.
Okay. Oh, your talk is not uploaded yet.
I did, but I'm screen sharing. Anyway.
Ah, okay. Cool.
So, one sec.
So let me give you presenter powers.
I already took it.
Okay, awesome. So, bye.
Can you see this? Hopefully. So this is sort of more. Has the power. This is not is going to be a long talk. I just want this to be more sort of a discussion. Because we traditionally had issues with the clone syscall in user space, and this is an attempt if we can make it easier for user space to use the clone syscall. It's important for us. For example, we maintain container runtimes and so on, and there's a bunch of user space applications that use this. Also, we added a new process creation system called Clone3, which is available since Linux 5.3. And by the way, before I go into this, Florian's reference was not to this talk on his slides, but to the talk we gave during Kernel Summit earlier. So if you're interested in the extensible syscall talk, then you need to watch it on YouTube because it's already over. Okay, so the idea is it provides a superset of the clone features minus some things we left out, so that Clone3 can be treated as a successor to Clone, and user space can move away from the, let's say, a bit awkward syscall layout of legacy Clone, because it has a bunch of different variants, as libc maintainers will no doubt be aware of. And it's an extensible struct-based syscall, which seen input from a bunch of users. So instead of passing arguments through the registered, we just pass a struct and the size, and it's versioned by size, and it's extensible, and it already has new extensions, clone HC group and clone clear sighand. And it's a syscall that is actually pretty heavily used in user space, and hopefully we can follow some links. Let's, for example, go to this one right here. I want to show you a little bit how this is used. You can see this. Yes. Maybe a bit too small. Should I?
Yes, make it bigger.
Oh. One more. So you can see that what user space often wants from it uses clone usually in a rather restricted manner. And as I told you, the legacy clone syscall has a bunch of different layouts depending on the architecture. I think these aren't even all syscall layouts, because I think it doesn't handle IA64 right here. But you can see, inline assembly to get the correct return value for Spark, and on ARM64 and so on, because this is not exposable directly in glibc, or not yet exposed in glibc as far as I know. And the idea is so that you get fork-like semantics out of clone. Let's switch back to here. And a bunch of other user space libraries do the same thing, or similar things. Lexi does the same thing. Runc does the same thing. I just listed a bunch of heavy users of this. Yes, basically clone same stack. Florian. Okay, and it's used in a bunch of other places. And next slide. Some observations we've made over the years is how user space wants to use clone. It often wants to use it like a fork-like wrapper, because this is sort of I guess this is the paradigm that people have grown up with, programming on Linux and programming in C. And so ideally they would want something like Clone3, you return a PID, and then you do if PID equals, you do whatever you want in the child, and then at some point you exit. But the glibc wrapper that we currently have exposed to user space in libc has this callback syntax, and I get why, because of how the stack is set up and so on. But it's not great. And here I'm already basically going into discussion. Can we add a wrapper for Clone3? Can we expose the fork-like wrapper for Clone3? These are the questions. Can we handle fork handlers and libc internal state cleanly? There has been a bug around this recently, or this is a long-standing issue, I guess, that people know about, that calling clone in multi-threaded environments, which tends to happen in shared libraries, you can run into deadlocks, you get issues with this setxid synchronization that Florian talked about, and so on. Because as far as I know, even for the clone wrapper, I think it's by now also documented on the man page. I think I added it a while back, that the fork handlers are not run, which can but then you can run into issues with that as well. What should we do about the stack argument? Should this be something that only glibc cares about, and we don't even expose it to user space at all? And can the kernel do something to make it easier to use and expose the stack argument? We've done some tweaks there. We are now always want the size argument. We do some validation. We have taken away the burden for user space to care about in which direction the stack grows, which the legacy clone handler does. But is there something that we can do to make this better? And now you can start screaming.
I would like to add something regarding the callback.
Yes.
And my feeling is that the callback isn't the problem. The callback actually, at least for a vfork style clone, where the caller has to be blocked, the callback expresses the semantics pretty neatly, in the sense that we do a bunch of stuff to set up the environment for this new function. The function runs to a point where it calls exit or execve in the before case. And then at that point, we resume the parent. That is basically, it is a callback mechanism, right?
Mm-hmm.
Where this thing breaks down is the stack setup. And I think what we should do is, if we add a wrapper for the vfork scenario, or the process creation scenario, then we should reuse the current thread stack. And basically that gets us everything, including guard page, set up for free. And at that point, it's very natural to follow the callback model, because we don't have to worry about the returns twice semantic, where part of the stack frame that calls clone might be clobbered by the process that the sub-process activity. Because if you have a callback function exposed as a regular function call with the semantic, then you just nest deeper into the stack, and you never reach the region of the stack that the caller expects to be not clobbered. So I think that the callback approach is the right semantics here for some of the use cases.
Right.
And probably all the container related spawn a new subprocess use case are covered by this model. It does not work with language runtimes like Python, or does not really work, because you then have to do a libffi style callback, but they are not really compatible with vfork or clone 3 in many fashions anyway. So I don't think that's a significant limitation there. Today you can call fork from Python, that works, but vfork is probably stretching things a little bit.
vfork is, for example, just speaking again, for the container use case, vfork is not really that important. I haven't seen it used in any serious container runtime. So.
That's because the container runtimes have fairly small process sizes. If you want to say, okay, I want to spawn a container from my JVM, for instance, then you really want to have vforks in there.
Yeah, that's true. Unless you're using Go, as Alexa's point, which is fair.
In the sense that you might have a large heap there. Okay.
Yes, more input. Yeah, sorry, the GitHub stuff was unreadable. It was basically just illustrating that that's systemd in this case, and a bunch of other runtimes even go so far as using inline assembly to get at fork-like semantics for clone and clone 3, and don't have to rely on the glibc internal clone wrapper. Well, the question is, I guess, Florian, you said that I wonder if we apart from glibc implementations, I guess you had a point about the stack argument being useful outside of library implementations. My thought had been that maybe we could not even expose the stack argument, but of course it becomes problematic when you want to do stuff like clone VM. Sure.
Yeah, I think there might be some use cases for like address sanitizer where you want to launch threads on the sides that the rest of the process doesn't know about. On the other hand, you can't currently use glibc there because you don't have a TCP that's compatible with glibc's requirements. So you have to disable single handlers and do a bunch of preparatory work. And yeah, maybe you're right. That is really not something we can support in C runtime libraries. You need to have your own runtime library to talk to the kernel anyway. So adding one more system call to that doesn't really matter, I suppose.
My point about the clone VM case is that we're not even in container runtimes. There is no, apart from JVM, maybe but the container runtimes I know about, we don't really care about, for example, a clone VM. We're always in essence, we're always reusing the same stack. That's why we want to have these fork-like semantics. What we care about are the namespace flags. Sorry.
Yeah, I mean, the same stack isn't a problem if you reuse the count caller. If you have the callback-based interface, then you don't have to do the stack switching. It's really, if you really want to launch a thread that the libc doesn't know about, then you need the stack argument. And you don't block. If you block until the caller return, until the clone subprocess concludes, then I think you don't need a separate stack argument.
You can't really, but you can't really safely spawn any threads via clone directly with glibc in the mix, I would assume.
Even if you could,
you can, but you can't use glibc on them in any fashion on the new threads.
Yeah, so it's basically unusable.
Not if you disable signals and use your own system call wrappers. And I think the sanitizers do that, and Creo does that as well to do some injection for its checkpoint restore operation. But that's not really my area of expertise.
I was going to say, if Mark's here, I think Valgrind also uses a separate thread because Valgrind has to wait for all C runtime threads to terminate before it can then do its final inspection of what's in memory and what's not. So there are uses for it, but boy, they're pretty minor compared to the broader use cases.
Right, good point. It's just that why I'm hammering on this on this stack thing is not, it's just an issue insofar as, because Eric is bringing this up as well, it's just an issue insofar as we always end up needing to allocate a new stack that we pass in through the clone system call wrapper. That's at least the most, that's the usage I've seen everywhere in user space so far. And that seems pretty wasteful. I think you can't get copy on write semantics with the clone wrapper that is currently exposed in glibc. In order to do this, we need to call clone directly. I think this one was one of the most more driving forces why shared libraries have their own clone implementation.
Josh, if you want to use thread local storage in the ELF sense, then you basically need to create call pthread create, and we would have to ensure that pthread create has the functionality that you need. We can't. I mean, we can't really enhance a clone system call wrapper to the degree that you can call pthread create. There's just an impedance mismatch between the two. That's just two different worlds, and either you have the full thread capability, or you have the clone at the other end of the spectrum. What we can do.
I was going to say I wouldn't necessarily expect a full equivalent to pthread create. I'm more just wondering if there could be a function provided from libc that would built-in port for setting up the necessary pieces that you would be able to tell libc, hey, I just made a thread. Could you please let me use TLS on it?
In theory,
without having to write assembly, I mean.
Yeah, in theory, yes, but currently we also have the issue with the ZXID broadcast and a bunch of other things where we basically need a global view of all threads in the process. So I think the idea is you want to bless the thread with a proper TCP in order to make it more useful for general use in the application. And there are a lot of moving parts, and I don't think in the current setup it's possible to do this.
Okay, so
I mostly feel like there's a.
What we can do is what we perhaps can do is we can provide system call wrappers that don't have a TCP dependency, so they don't use Erno for our reporting, and those would then be safe to call after clone without a TCP.
Yeah, so you're saying we provide, like as we discussed in the wrapper talk just before this, we provide
Exactly.
no Erno variants of those syscalls, and then the runtime can say these are the following things I can call it. I know I'm going to touch the TCP and the static TLS or any other TLS allocated. Yeah. I mean, the alternative is you register the thread, but if you register the thread, libc is going to take over a bunch of stuff. Like we have to set up the right signal handlers for the setXID handling. Unless we get a syscall for these things, for more of these things, but.
And the thing is, we don't really know where clone 3 is going to evolve in what directions and what kind of things we need to do to integrate that separate execution thread into the rest of the process image. And currently we need a style integration for a bunch of things, unfortunately.
So I guess one of the things I want to raise is we've been talking for a long time about this concept of like execution agents. And it seems like what we're trying to break down here is kind of the minimal number of operations that like creating an execution agent would require and how the runtime can help you in any way. Or because like if I had to do this, like, libc could provide some of these interfaces, but if I view them, I feel like viewing them from the lens of, yeah, the user has this runtime and they just want the thinnest execution agent possible. How do they get that without having to write everything in assembly? So, and I don't know if that even falls to libc or if we just have to write execution agent library that just does all this stuff or does some of this stuff.
I guess you need someone to write the wrapper, right? Yes. Should probably look into that.
Wait, were you at Florian's talk before this?
Yes. I was, indeed.
Actually,
I was at his talk, he was at mine.
Yeah. DJ Delorey's on the call, but I promised Florian that this year I would write more wrappers, and that he would sit behind my back and critique my wrappers that I write. So I definitely have promised to write some wrappers this year. I don't know if I want to write the Clone 3 wrapper though.
Yeah, I mean, this is one of the things that has kind of held me back, right? When I looked at the old clone wrapper implementation, it just looks like custom assembly for every architecture.
Yeah, but that's going to be the same, I suppose.
Yeah.
Because of the callback handling we need. That it's not going to be too hard, I think, and
no,
I think it's worth the effort. And we would even use the wrapper internally in glibc.
Yeah.
In some cases.
I've done I've done a prototype of this a while back, but then never brought it into any upstreamable form. And even in user space, I think Creo already has a callback based Clone 3 implementation for at least ARM64 and x86.
Yeah. Well, but I mean, if I were to, I think anyone who writes this wrapper basically has some due diligence to do, which is to go out to all those other projects and find out what they were doing and how they were doing it and why and what kind of semantics they were expecting and like how they wrote their wrapper glue around it to see if whatever we write in libc would actually be useful to anybody to use, because it'd be a shame to just write this wrapper that then nobody ends up using and they keep their old code and it provides no simplification to the rest of the runtimes that are using it.
This is exactly like some people at the beginning when we did Clone 3, they were like, this should be a complete redesign. And fortunately, Linus agreed with us that, I'm turning on the light, sorry, that we make it a superset so that you can actually move from clone to Clone 3. Otherwise, you don't see any adoption in user space, and especially for something where basically any thread implementation needs to rely on clone, I think it needs to be worthwhile. And hopefully, Clone 3 should give you everything that you need. I mean, when we added it, I looked through a lot of user space and looked how they pass flags. I think what you will end up doing, that's just my impression, is there are a bunch of flags that Clone 3 will not allow you to pass because they have never made any sense. They have been deprecated. So you probably need to strip off some flags that get passed in, because some people just pass through, I don't know, clone detached and just because it has always been done that way. But otherwise, this should work. What's been busy on in the chat?
We're discussing fixing the setXID problem. But I think that the issue is that, I mean, I imagine there's going to be a lot of interesting locking problems when it comes to moving creds from being task struck to being shared. That'll be my first guess of list of issues that we're going to have to deal with.
Yeah.
It wouldn't be moving them. It's more just moving the logic of setting all of them into the kernel so that you don't have to go signal another thread to go set its own ID and deal with the fact that signal handlers themselves are interesting and not something that they're a shared resource. So
I think Andre just volunteered to write the Clone 3 wrapper because this is the Creo wrapper he talks about, including the callback. They've already done the work. See, that's a he's making a smiley face. That's agreement. But yeah, I mean, if people don't have any other issues to discuss, then I'm mostly done.
I was just wondering, could we split the stack usage into two halves, right? Can we, like, if we have to expose something like a wrapper, can we split it in two? Just wondering if there isn't one way in which you can basically clone, and then a second pass you basically can call the callback and give it a new stack if you wanted to. The way sig alt stack might get handled. I have to think about that. Because conceptually they're two different things you can do. One is this clone with your closure, and then it has all the information in it. But then if you're still if you're still sharing a stack, you then need to then leave that stack in some way, and that sometimes has compiler implications and double return issues. And so if we split it into two pieces, maybe the idea is clone 3 gets exposed as two wrappers. One which does everything clone 3 would do, and the other one which lets you walk through that callback into a separate stack. But I don't know what that would look like.
Interesting. We should move this discussion out of the chat and.
I was gonna say Oh, sorry.
No, go on.
I was just gonna say for the CRED thing. The other thing is that current CRED is accessed all over the place in the kernel, and having other people be able to change it probably is going to cause some interesting issues, right? I mean, it's the same with That'll be my guess. Again, my understanding of this code is quite surface level, but at least to me, that seems to be like the most immediate issue is anything that does anything with the CRED struct is gonna not like it. Well, because another thread can always just sorry, to Jeffrey's point, yeah. I mean, like, but any other thread can be executing while another thread is in a system.
The other approach would be, I mean, we have other thread attributes where you can configure whether they are shared with the parent thread or the creating thread or not. So maybe the answer to that is to patch the CRED object directly or something like that. I looked at this and I basically gave up when I noticed the current CRED issue you mentioned, because it looks fairly scary. What would already help a little bit is if we have a primitive, a system call where we can run code on a different thread, where like a signal, basically like delivering a signal, but using the calling thread for storing the signal context.
CPU OPV, isn't that what Mathieu Desnoyers' work was, which is to run a small block of code on another CPU?
Yeah, but not just not just a small block, but basically arbitrary user space code to a context switch. Make sure that the target thread is sort of stopped as if in a single handler, but not actually touching the stack of the target stack, but using a different memory area. And then some of the issues with setXID go away because it's safer to do the system call, the setuid system call, because you can't really blow away some small stack or hit a scenario where the application has disabled the signals and doesn't expect a signal handler to run. But what we do in glibc is, in order to make sure that we can always change the user IDs, we actually block applications from changing the signal masks to block our specific special signal for the broadcast. So we trade one incompatibility for another problem there. And maybe, yeah. So if you say, okay, I don't expect any signals, and you block all signals, then you still get the setXID signal at that point. And that could be bad depending on what's going on. Yeah, we have two reserved signals. We have the ZXID broadcast or basically 3 operations and 2 signals. ZXID broadcast, SIG timer for timer create. I'm not even sure if we need it, and p-thread cancellation. That's what we reserve. We actually have an API for reserving signals. So you can call an allocation function and you get a real-time signal number back. But I've never seen anything using that. But in theory, you can actually have multiple libraries coordinating this way and make sure that they all use distinct signal numbers for their stuff. And it's also not going to overlap with the glibc signal number.
Yeah, we may be going down a rabbit hole here talking about.
Yeah, sorry.
No. Removing ZXID, it just becomes one of those things where if it wasn't there, then it would make it easier for a runtime to request an execution agent, which is a kernel thread that's running in user space that has some kind of properties that it can call into C. I do like the idea of the syscalls without errno that you can call, so that if you make your own thread with the wrapper, you're like, okay, I have these operations I can do, and they're the only things I can do. I really do think, though, that whoever's writing the wrapper, we have to do a review of how people are using it, so we make a decent wrapper that people are going to use. It's going to be useful.
Mm. Indeed.
Laughing at the Erno foot guns reference, but
Yeah.
Yeah, no, I mean, like the foot gun everybody forgets is that if you change Erno in the syscall, in a signal handler, you have to restore it. Nobody remembers that one. Yeah, I don't have anything else to add other than, this is going to be an interesting wrapper to write. I mean, this is kind of why some of these wrappers stall out, because it's one thing to write the interface, and it's the other thing about like how do all the runtimes use it.
Yeah.
Did you watch Michael Karisk's how to write a kernel API talk before you wrote your APIs? That's kind of mandatory watching.
We're in close. Yeah. We did, and also we're in exchange because he has some good points. And the extensible syscall talk that we gave was one of the things that we wanted to do and that we want to formalize, and that basically everyone who attended the session was very much in favor of, is stuff like no more multiplexers, putting it into the docs, how extensible syscalls are going to be used, in what shape and form, and so that we have a bit more standard in the kernel on how to design system calls, and also document unsigned int and size t and some of the worries that you have, so that because we still have syscalls proposed. I caught a few recently that, for example, added an unsigned long as a flag argument and so on. And you end up telling the people, don't use unsigned long, use unsigned ints. And we basically want to have this documented, and then can take this and send it to someone and say, hey, it seems you made a few mistakes. You might want to check this document where it's outlined how to design syscall in a bit more detail than we're doing it today. Yep. But it's been really great, by the way, that's interacting with LPC in recent years on the mailing list and so on. And there's a lot more exchange going on, I feel, than used to before.
Yeah, thanks for writing emails to the list and responding to stuff. So.
Thanks for providing input on so many things that we do. It's good. Okay, I think this is it.
Okay, thank you very much. And well, we have 7 more minutes in theory, but if there are no more questions or anyone wants to say anything, then I guess that we are wrapping it up.
I'm just trying to get everyone into the beer buff right at 8.
All right. Okay, so then it's party time. So thank you very much to everyone for for attending the micro conference, and well, I guess see you next year wherever it is, or the web browser. Who knows? Ciao.
Thank you, everybody.
Thank you.